So it's streaming? Yeah, okay. So welcome everyone, and this is with a great relief that finally we can start our presentation. I'm a little bit jealous because three quarters of the crowd here is on holidays and we are just the one being punished here. So I will talk about, so I'm not very good at titles, so basically I will talk about, I don't know what the title means really. What I want to talk about is about finite state transducer. And it may seem a little bit strange that we are talking about this because finite state transducers were used in the past, almost 20 years ago, and it seems that there is some kind of regain of interest over the last past years. So we have gathered a team here at the workshop, and you see that there are many people that are actually thinking it's not such a crazy idea. You have also heard a little bit about finite state transducers this morning, so it seems that it's something which is not completely dead, let's say. So, but maybe for people that are still having a hard time to really understand why finite state transducers are still something today when we have all this end-to-end technique, let's take a little tour about like the status of ASR system nowadays. So these are not results of the workshop, these are simply some results I've cherry-picked from a benchmark run by a French team in Grenoble. And it shows the water rate on, so they are measuring a bunch of things for large end-to-end system. And as a baseline, they actually took a CALD system, so hybrid decoder. So hybrid here means you have a TDNN system and then you have a FST-based decoder. So that's the FST, where the FST come into play. And actually, if you look at it, you realize that the water rate is far from basically validating the assumption that end-to-end systems are always consistently better. And if you look at the classical features, the water rate, the gap is actually huge, and even after a lot of effort of putting a lot of like pre-trained system and a lot of training data, at the end of the day, you still get better system with a hybrid approach. So at this point, you may say, well, this guy is not serious, he's not doing ASR on Libre speech. Okay, point taken, but we can look at something different. So we can talk about the practicality of ASR of hybrid system versus end-to-end system. An end-to-end system basically means that you have one system for the task, or let's say in the current, in the jargon we use, behind the term end-to-end, we basically mean a monolithic structure, which basically means that you have, for each task you will have one system, and you have very little opportunity to share parameters between tasks. So if you have ASR system, then it means you need to train an ASR system to collect the data for the very specific task of ASR. If you have a keyword spotting system, you want to build a keyword spotting system, again, you need to go through the hassle of building a system that will be targeted for keyword spotting. And the sharing, of course, you would like to share parameter between the ASR and keyword spotting, but this sharing of parameter has proven to be relatively challenging. On the other hand, if you're going for a FST-based approach, a hybrid system, everything is kind of smooth, right? You can share a pre-processing step. We used to call it the acoustic model. Nowadays, the acoustic also embeds some linguistic information. Then you have some kind of universal representation. Here, some FST-based representation of speech, and then you can have some downstream task that will have a smaller weight, smaller size, and less difficult to train, and requiring also less data. So we can also look, in terms of practicality, we can also look at where speech technologies are actually developed or used today. As a scientist or researcher, either in academia or in companies, we often are accustomed to have at disposal farms of GPUs a lot of computing resources, whether it's CPUs or GPUs. But the fact is, we speak everywhere when we travel, when we are in a plane, in a car, somewhere, and this is where the speech technologies actually needs to live. And on all these environments, we have much less computing capabilities. So if you want to have an ASR running in a plane, maybe you can't really assume that you will have a connection to a server with a lot of GPUs. And once again, the whole end-to-end paradigm is kind of suffering because we have hard time to control the size of this model and also the complexity. FST here in this context can, in my opinion, also play a role. I'm not saying this is the whole solution here, but it can at least have a very fine-grained control of the computing resources at a given time for a given environment. So I can go on and start to make a list of what's good for FST-based approach or hybrid system and end-to-end system, and some will give me counter-arguments. At the end of the day, we are using end-to-end system, and maybe for a good reason too. The main reason, in my opinion, is FSTs or hybrid systems are extremely complicated to build. For the less younger of you, if you have ever built a Caldi system, a Caldi recipe, you remember how kind of complicated that was. And for the less younger of you, you can remember that before Caldi, it was even more complicated. So hybrid systems have kind of a steep learning curve, and that are very hard to democratize. On the other hand, end-to-end systems are extremely easy. I can take any people, any engineer which is not very familiar with speech recognition or technologies in general, and in a couple of days getting him training ASR system or something related. So we can really see this from a historical perspective. So the hybrid system were basically set up in a as early as the 90s. So basically in the 80s we have the TDNN system, and in the 90s we get the connectionist approach, and then the little bit more refined then by the WFST framework. But basically 20 or 30 years ago, then we already had a hybrid system, and the community is already convinced that this is a code solution. But as soon in 2010 that we got tools that make the training of neural network much easier, kind of simplifying the whole pipeline, then we started to abandon the WFST to the profit of end-to-end system. So here, this corresponds to Theano, to CNTK, to PyTorch. These tools have kind of lowered the access barrier to neural network and end-to-end system, making the whole training much less painful at the cost of like having less modular pipeline and sometimes more complicated or less accurate training and decoding. So the objective of this workshop is really to say, well, we don't want to abandon, I don't want to give you the impression that we should right away give away a neural network and an end-to-end system. That's not really my point. My point is maybe we have lost something along the way. Maybe there is something in WFST framework that still is lacking in the neural net-based pipeline, and we want to bring it back to really get even more powerful system. So the objective of this workshop is actually quite simple. We want to have a happy marriage between large neural network and FST network, and FSTs, simply FSTs. So we can imagine that maybe I want to have a neural network where at somewhere in the middle, somewhere in the layer, I want to have a little bit more control here, and maybe I want to have a FST layer, and I want to be able to train this system, so that means I need to be able to run some algorithm on GPU on FST, and I need to have the gradient to flow, so data to flow the FST, and to be able to backpropagate to my FST, sortable as a neural network layer. So, in one phrase, we want to make FST great again. And of course, this is quite ambitious program, and fortunately I was not alone, but I was accompanied by actually a quite incredible team. I won't go through the names one by one, obviously, but I want to give some special thanks. First of all, I want to thank our godfathers, as I call them. I mean Lukáš Borget, I mean Dan Povey, I mean Michael Riley, and Cyril Alozan, which is here today, because these people have made great contribution to the field of ASR and WFST, and I have to say the world looked nice when you're sitting on the shoulder of giants. So thank you guys, it was very nice to have you here. I also want to give special credits to Kay and to Corey, because they have been extremely patient with students. Students have the bad habit to ask too many questions, and they were here to answer the question when I'm too busy. So you guys, thank you. And I also want to thank all the team. It was quite funny actually to be with you. Everybody was putting picture of like how cool they were. They were going to beers, they were going to dancing, I don't know. And I look at the picture we had, and it was only whiteboard with equation. So that's the coolest picture I found. I'm really sorry, we are nerds. We have to live with that. All right, so that's after this long introduction. So this is how things are going to happen. So as for the previous presentation, we'll have two parts. The first part will address the problem of trying to make FSTs compatible with neural network, and we'll try to focus on two things. How can we make them, let's say, GPU or accelerator friendly, and how can we actually use modern tools to differentiate through them? We also have exploration of concrete use case where some of the people who present work where they use FST to learn pronunciation of new words from the acoustic, and also to train early exit models, so having model capable of scaling depending on the computing resources available, and to have better training and better performance thanks to the FST framework. In the second part, you will hear about many interesting things. You will hear about, let's say, LAST. And then I won't spoil too much what it is, but I want to say this is a nice way of looking at speech from a unified perspective, and where FST is a cornerstone of this element. So you will start to see that you can really very easily modularize your pipeline, and you can have one representation which fits nearly all the speech application with it. Along the way, you will get a special focus on streaming and long-form ASR, where we do believe that the WFST play can be significantly better than traditional end-to-end system, and we have some good reason to believe it, and many more. So without further ado, I propose to come with me and to actually enter the wonderful world of tensor-based FSTs. So I need to give some credit, and it would be wrong of me to make you believe that we are starting from scratch, because we are not. Actually, there is a long tradition of research of WFST, and I want to mention the tool OpenFST, which many of you know and has been and has made the success we all know, and I will consider it as a baseline in most of our experiment, or not experiment, but eventually algorithmic complexity. I will report later on. I also want to mention two more recent works. This is GTN. This is a graph transducer network from Oni Hannon. At the time, I think it was in Facebook. And another one, which is probably a little bit more known, this is K2, which is made by Dan Povey, who we were lucky that he visited us this summer. And these two toolkit, GTN and K2, actually share a little bit the same idea, and which is to try again to make WFST kind of easily to fit neural network. So the idea is the same problem, to make them compatible on GPU and also differentiable. They have reached some success, but it's not enough. In a sense, they are making some not approximation. They are taking some subset of functionalities. They cannot really make the whole FST framework compatible, so they will try to make some choices and basically to specialize a little bit their tools to the applications they need. So we were largely inspired by these tools, but we wanted to get the whole thing. We really wanted to get the whole FST framework to be fully compatible and without any restriction, and this is where our work started. So here, I will repeat again, but the main challenge for this tensor-based FST or linear algebra FST is to really to solve two or three problems. The first one is we want parallelizable algorithm. And we focus so much on the problem of parallelism because we want to be able to fully benefit from GPU. If we have any tools that cannot fit on GPU, then it is outside of the neural network world. So that was a big focus. The second thing is to make sure that we are able to propagate gradient, and this for the same reason that if you have a function or whatever it is that actually is not able to, that blocks your gradient, that's pretty much useless in the deep learning community. I added a third bullet, and it's a little bit hard sometimes to justify it or to measure it. But I also think that there is that this FST framework is kind of difficult to access. So it's very subjective. Some people maybe find it's easy. I don't think it is. And we also try to make it simple. It's not easy to make things simple, but we try actually to add some abstraction layer to give, let's say, a new perspective and perhaps a better understanding. So let me start, and this on the right side, on the left side, sorry, here you have the classical formulation of FST. So you don't need to read everything. What you need to realize is basically it's defined in terms of a set of transitions. So basically, the classical way of approaching FST is simply to think that we have a graph with a little bit more of extension, a little bit of added features. And we decided to take a different route, and we say, well, we'll encode the same information into 3 objects. You have this M, so well, the M here is back. I don't know where it is. All right, never mind. So you have the M, which is a tensor. That's just imagine a matrix of matrices. It has 4 dimensions, and it will encode all the arcs. So the dimension will reflect the number of input labels, input states, output states. And the alpha and omega are basically the sort of FSTs we allow to have states to be a little bit special. They will have a bunch of what we call initial states, states from which I can start the computation, and final states, states that can have that can end the computation. So this is how we encode things. So this is a very typical graph, so FST machine that we represent as a graph. And the way we'll encode things is for each pair of labels, so let's say AX in my examples, we'll have a matrix so of index AX, and this matrix will encode all the weights of the arcs for every pair of states. And the same thing goes for BY, you have it here, and the alpha and omega will store, as I said, the initial and final weights. There are more matrices, actually. There are matrices for BX, for AY, and so on. I don't show them because they are just full of 0. And the first thing maybe to notice with this representation is that we are talking about objects that are mostly filled with 0, and not just a natural 0, the 0 of a semi-ring. Just think of basically numbers here. We have allowed to do only 2 operations, one which we call multiplication, the other is addition. So you need to think of them as matrices, but a little bit weird because they are not working on real numbers. So the main thing, as I was saying, is that these tensors, these matrices, are actually completely full of 0, and you start to store this thing in memory, it's not going to work very well. So what we want is simply to have a representation that will only store the non-zero value, or the semi-ring non-zero value. So this is already a well-known problem. So this is basically using sparse tensor instead of matrices. And we can do it relatively efficiently. So the main question we started to think when we started this work is simply to say, well, we are going to need to store this tensor object in terms of sparse matrices, and we wanted to make sure whether we had any loss of performance, whether we compare to traditional approaches. So the first line, this list of lists, for instance, is just like the way we store things, let's say in OpenFST, and what you say is like, you have a certain complexity to iterate over all the arcs, and this complexity will impact your algorithm. If it's too high, then your algorithm will be very slow. And the main message here is it doesn't really matter whether if you have a classical graph representation of sparse tensor, the complexity is always the same. And of course, if you have a dense representation, then the memory blows up, but you get very fast access. I want also to make a special mention here because as we started to work and compare with what, for instance, was doing K2, we realized that the format we are actually using for many algorithms, which is compressed sparse fiber, the name is a little bit crazy, but the idea is simply to sort and to compress repeating elements, is actually a generalization of what Dan calls the ragged tensor in K2. So what K2 is doing can be actually understood as a special case of this framework. So here I was a little bit playing among the compression because you have some compression, and we were just measuring whether we are paying a little bit like our representation compared to traditional approaches. So the white line, the dark line is simply the classical way of storing a FST is just storing the arcs, and we see that depending on some choices how we represent the tensor, we actually can get a little bit over or sometimes a little bit less. But at the end of the day, we are not losing anything here. All right, so we have basically solved the first problem. We have decided to look at FST from the tensor-based representation from kind of linear algebra perspective. And the first question that arises that was it efficient to store them like this? Well, clearly yes, we can have as good iteration access and as good storage as existing approaches, but now what about operation? Because that's the main thing. For FST, we want to manipulate them to build a more complex graph, more complex FST, and to do some inference like calculating the shortest distance on something else, and so on and so forth. So in the rest of this presentation or this part, we'll try to address relatively quickly all this operation, and we try to answer two questions. What is the work and what is the depth? The work is the complexity of the algorithm. It's how much work you have to do to complete the algorithm. And the depth is number. So imagine that you have a machine with as many processors as you want. It's an ideal GPU. You have 3 trillions of processor or even more. Then if I give you an algorithm, the depth answering you what is the longest sequence of operation the one processor will do. In a sense, if your algorithm is fully parallelizable, your depth is 1 because every processor will just do one operation. If the depth is more than 1, it means that in your algorithm you have dependencies. To obtain the output of your algorithm, you need to make a sequence of operations that cannot be fully parallelized. So you want the depth to be as small as possible, and if your algorithm is not parallelizable, then it's equal to the work. So I will go a little bit quickly for this union concatenation and closure. Just so these constructive operations are extremely easy to express in this tensor base because we are just building block diagonal matrix, stacking vectors. So this is extremely easy. This has a depth of 1. It's parallelizable. It's boring. Okay, so these are done. Maybe I can just show you the closure here because it also shows a little bit the idea is a lot of things here. We are creating art just by multiplying vector. And once again, this is what we wanted to have, is to add this kind of abstraction layer where we think again about our graph and just manipulating objects that we are accustomed to and we know that will be very suited for any computing environment, GPU, CPU, and whatever. All right, so now let's look a little bit at a more interesting algorithm, which is the shortest distance. So here by shortest distance, I'm actually asking to compute the sum of all the path weights. So you take a machine, you go for all the paths, you could get the weights, and you sum them all. And that will give you the shortest distance. This algorithm is extremely important because when you do, let's say, the forward-backward in HMM, well, that's the first step of the algorithm. When you want to do decoding, well, that's this algorithm again. So basically, every inference operation will necessarily at some point compute the shortest distance algorithm. So the main formula is here. This is this one, and I'll try to parse it with you. The first thing we need to do to look is maybe at the tensor here, so this M matrix. So here we are summing, because in the shortest distance we care about the path but not about the labels, we are simply summing every matrices together, just dropping the labels. We end up having a single matrix. The second thing we do is we take the closure of the matrix. So here it means x, so taking the matrix and getting x power 0 plus x power 1, and so on and so on and so forth. So the idea is like with this closure, we are actually computing the cost of having paths of length 0, paths of length 1, paths of length 2, and so on. So we are iterating over all possible lengths of paths. And at the end, we are multiplying from the left and right by the initial and final weight only to get the weights, the paths that are actually starting from a correct state or for initial state and actually ending in a final state. And that gives us our computation. Of course, naively computing this guy would be a little bit not the ideal solution because you would just waste your memory and probably not being very fast. Fortunately, we can actually have a linear program that actually computes nicely, and that's the result we get here. So this is typically in all parlance, I would say it's a kind of token-based decoder where we just, at every time step, you actually propagate the tokens through the state of the art. So first of all, let's talk a little bit about the complexity here. And the Q-based algorithm is the complexity for the Q-base is the one of OpenFST. And you see that they have spent quite some time and the algorithm is linear. Our algorithm, the algorithm I just described, is not quite linear actually, because we didn't have yet make use of the structure of the matrix, so we are still working on it. So we know that basically we have a quadratic. In the worst case, the complexity for algorithm will be quadratic. But there is a good news, whereas a Q-base has basically a depth which is not redefined because it's extremely hard to parallelize a Q-base algorithm, we have actually a depth which is basically much lower than the work. It means that we can really benefit from the parallelization. So this plot was obtained by Yenda, which is here and which is today is awake. And so this is 5 minutes after he gave me the result. So it was, I want to say that it was a little bit painful to obtain this result. So the blue line corresponds just to the time of computing measured by OpenFST. And on the x-axis, you have the number of arcs, so the complexity of your machine. And as one might expect, as the number of arcs grows, so the scale is logarithmic, then the time explodes. The orange line corresponds to an implementation of this algorithm with our tool, but on a single thread. So you see that the speed up, the orange line is decreasing because after some time the size is too big and the algorithm is not efficient. So basically it will just be much smaller, much slower than OpenFST. The gray line is the same thing, but this time we use a GPU, so we actually parallelize like crazy, and we just use as many processors as we can to get the result, and we see that the depth, having a depth which is much smaller than the complexity, actually pay off, and we can compensate the quadratic complexity of our algorithm. And now I will finally leave the floor to Tina.
Yes, hi, I'm Tina. So let's say we have a weighted finite state machine, and we would like to redistribute part of the probability along its paths without changing the whole weight of the transducer. So a simple example of this actually is the weight pushing algorithm that is used during decoding. Now, as you know, you can do this reweighting either from the final state towards the initial or vice versa. So here, we are basically presenting the linear algebra formulation of a reweighting towards the initial state using our tensor FST representation. So as you can see here, for each pair of label, we have this matrix that has in rows the source nodes, in columns the destination nodes. And just as a reminder, if you would like to take this transducer and reweight it towards the initial state, then basically what you do is to take the weight of an arc multiplied by the reverse of the potential of the source node and then multiplied by the potential of the destination node. This is what we do. So let's say we have a vector D that has the potentials of the nodes, then we can simply define our reweighting by a matrix multiplications as follows. So we create a diagonalized matrix that has this vector. We need also the inverse of it, and then simply the new matrix that will basically substitute the old one is obtained by this multiplication. Now, if you want to reweight on the other direction, you would just reverse the order of these two matrices. Now, for returning to the example that I did, if your D vector is having the shortest distance at each node, then you get the weight pushing for free. So what is now the complexity? Let's say I do not treat the complexity for calculating the D vector. Then for the sparse case with E number of the arcs and Q number of states, then our complexity is just in the order of sum of the two sets cardinality. And if you think that each element of your matrix is just a block, then this is fully parallelizable, which means that it has a depth of 1. And at this point, I leave to Pablo, who will talk about the composition.
Hi, everybody. I'm Pablo. First of all, I want to say that before working on this project, I was not very familiar with FSTs, but the linear algebra framework where we are working on make it much easier. So I think it's something to mention because it's one of the points we want to work on. So I'm going to talk about composition. Composition is very important when we are going to combine acoustic models and language models in the coding. Just a quick example. The idea is we have 2 machines, and if this machine is taking some input and will give some output, and then we pass that output over this machine, we will get something else, and we want to build a new machine C that is equivalent to doing that. So for example, here, if we start with an A and we emit a B, and in this case we receive that B and we end with a C, here we see that case is A, C, so the B is matching in this case and this case as this output label and input label, and so here we don't have the B, but we have the complete transition. So that's what we're going to do, and the classical way of doing this is moving through all the possible accessible transitions in the traditional queue-based algorithms and finding which labels match. But we're going to do it in a tensor fashion. So we have this tensor as described before. These are the input labels, these output labels, and this is number of states. So what we're going to do is, for a given pair of, this is the final tensor of this, the input tensor, and this is the second, this is the first machine, and this is the second machine. We make the composition. So for each pair of labels, we're going to sum the result of this operation, which is the tensor product or Kronecker product, and that's it. In a sense, we are going to compute many more transitions that are not accessible, but it's okay. This is the same way of writing this, but in indices notation, which is more convenient for programming. We just need to do some reparametrization here of these indices like this. So the linear algebra way of doing this is convenient because we can write more or less the equation in paper, doing some operations, and then going through the code and try to build the same thing. And this is just the Julia code that we are using right now. We are using this tensor, sparse tensor representation that Luca mentioned. And here we have, for example, this is not the Kronecker product, this is just the semi-ring multiplication, but this is the part which combines all transitions. And this is the summing that was in the slide before. So one nice thing to see is that this algorithm like this is not in a parallelized fashion, but if we don't care about this accumulation, it's completely parallelized. So when we work out the complexity of the algorithms, this is the complexity of the composition for the queue-based algorithms, which has this dependency on the accessible arcs. But for our case, we have the dependency with all the arcs, which is much higher in many cases. But the good thing is we are able to parallelize it. So in the worst case, we will have a depth of that depends on the number of arcs. But for some special cases, with like for example, we're not doing composition, we're doing intersection, which is composition in acceptors. The depth will be 1, so that's really good. So we implement all of these algorithms in CPU, and also for this case, for the intersection we're doing in GPU, and we have some benchmarks. We generated a lot of FSAs, random FSAs with different numbers of states, arcs, and symbols, and we ran it, our algorithm TensorFST on CPU and CUDA, and compare also with K2, and we are showing the speed up related to OpenFST, which is 1 here, this red line. So if we are below that, we are worse than FST. For the CPU version, we are a little worse. But for the same thing happens to K2, but for the CUDA versions, both algorithms are much faster. Wait. And one interesting thing is that we also compute for a real example, not a random FSA, just a 10-second speech utterance composed by a 5-gram language model, which is this dot here. So in that case, we are actually at the same speed that OpenFST, and we didn't have that result for the CUDA version, but we will hope to have it soon. And that is time for Cyril.
So I'm Cyril, and we talk about epsilons. So epsilon transitions are actually very useful because they allow for the compact rotation of a wide range of FSTs, such as, for instance, language models. But they introduce some delay in processing because you might need to follow a very long epsilon path before reaching the label, the non-epsilon label you care about. So traditionally, there's two approaches for epsilon removal. You can, for a given non-epsilon transition, you can either add that transition as an incoming transition at every state that can be reached by an epsilon path from the destination state of that transition, or you can add it as an outgoing transition at every state that can reach the origin state of that transition by an epsilon path. And both approaches can be very naturally implemented using the tensor-based formulation. Basically, you need to compute the closure of the adjacency matrix for the epsilon transitions, m epsilon star, and then you can multiply that closure matrix with adjacency matrix for each pair of non-epsilon labels, either on the right or on the left. And that gives you the two approaches. And then you also need to deal with the initial and final state accordingly. So the complexity is going to be dominated by the computation of that closure of m epsilon epsilon star. And this can be viewed at performing Q product of a vector with a closure of a matrix, which is basically what the shorter distance algorithm was doing. So the complexity would be Q times the shorter distance algorithm complexity. Which is what we can show here in the graph, but we saw that we still get a reasonably small depth, so we can still benefit from parallelization to some extent. We also looked at combining short distance with remove epsilon. So the idea is, can we compute short distance on the epsilon remove machine from the tensor representation of the original machine A? And this is what you can see in the formula. On the left, you have the definition of short distance of the machine A prime, which is epsilon remove 1. And on the right, you get what you get if you put the formulation from the previous slides, except we can move the closure outside of the sum. And to do that on demand, it's relatively simple. We need to be able to implement the sum over all the mij for an arbitrary tensor, and this can do it on demand, and also compute the closure on arbitrary matrix T on demand, even when the matrix T itself is also computed on demand. And this idea can be used to combine short distance with some other on-demand algorithms, and we're looking at using that for composition. So now let's step back and look at where we stand on complexity for all the algorithms that we presented. So in most cases, the story is relatively good because the complexity is the same as in the classic Q-based implementation, but we get this very low depth. There's only two exceptions, which are short distance and remove epsilon, where this time we get a worse complexity, but we still get a relatively low depth that allows for parallelism. And we're looking at improving this algorithm by taking advantage of the structure, as Luca mentioned. And now let me hand it to Martin.
Thank you, Cyril. Yeah, so I'm Martin, and I'm going to talk about the toolkit we created during the workshop. So the toolkit is called TensorFSTs.jl. Does it work? Okay, it doesn't. Okay.
You need to make it. You don't have slide. You have the demonstration.
Yeah, no. Let's. I will continue. So the toolkit is called TensorFSTs. It was implemented in Julia. It's publicly available on our GitLab. And in the toolkit, we implemented all common FST algorithms, or all the presented algorithms which were presented in the previous slides. And the operations are also automatically differentiable, just due to the fact that they are expressed in the linear algebra. And also in the toolkit, we allow users to define their own summerings. Okay, so now let me switch to the demonstration we prepared for today. No. Okay, so no. So I have to express that the toolkit is still under construction, so there are some parts which are not still available, but the prototype we built so far should be suitable, should be sufficient for today's demonstration. So in the demo, I will use two symbol tables, drinks and moods, and I will also use a tropical semmering, which is a semmering type from our library. And the tropical semmering in our library is defined in a following way. I hope it will work. Okay, so I will explain. So the semmering 0 is basically the minus infinity. Semmering 1 is 0. And the semmering addition is just taking a minimum of two values, while the semmering multiplication is just a natural addition of two values. Okay, it's very crucial to express this, so you will understand my demonstration. So here I'm defining an acceptor with 4 arcs and 3 final states. And I have also another example transducer where I have 4 arcs, 2 final states, 1 recursion, and we can actually interpret this transducer as a drinking FST, where someone feels better after drinking 1 beer or 1 wine, and he feels even happy after drinking another beer, but he starts to feel sick when he drinks more beers. I take this example from Honza Černocký's lecture. Okay, and now let me show you how the composition is done in our toolkit. So in the composition accepts 2 arguments, A and B. So these are the examples I already showed you. These are the transducers. And in order to do the composition, we need to permute the dimensions of our transducers due to some optimization reasons. So the resulted composed graph has the following form. As you can see, we have only 2 valid paths. So this is one and this is the second one. And all other paths are not valid just because they don't start from the initial state. Okay, so we have only one initial state. And we can also compute the shortest distance in this of this composed graph or transducer. And as you know, the shortest distance under the tropical semmering is just the cost of the shortest path. And the cost of the shortest path is this one, and it's just a 0. And also, in this demo, I would like to show you how easy it is to compute the gradients of our operations. So we just call the gradient routine, and we are computing the gradient with respect to our transducers A and B. And here is just the body of the gradient, which is the composition followed by the shortest distance. And here in these figures are the resulted gradients. So this is the gradient with respect to the transducer A, and here we have a gradient with respect to the transducer B. And as you can see, the gradient under the tropical semmering, or the gradient of the shortest distance under the tropical semmering, is just a best path. So we basically we implemented shortest path without much effort. All right, now I will move back to our slides. Yes, it's we don't have internet connection.
We're not connected.
Yeah. Okay. No, we are already back. So we are back. Okay, perfect. So okay, we didn't. So in this presentation, we didn't talk about the determinization of the algorithm. We actually don't support it now in our toolkit. But instead of implementing the determinization, we are using the OpenFST. So what we did is actually we created OpenFST Julia wrapper. It was actually Mike Riley who implemented this. And the Julia wrapper, the OpenFST wrapper, is also available on our GitHub. And we use this wrapper for all operations which we don't naturally support in our toolkit. So you can use our toolkit for determinization, but it's actually running the OpenFST version. Okay, so that's it, and I will pass the word to Corey.
Thank you. So we're the first use case of some of these tools that our colleagues have described. The one that we're working on we called Sounds Like, and it's about the pronunciation of rare words with respect to training data and some of the challenges that causes and trying to alleviate them with these tools. So there's two things that make pronunciation difficult. One is what I'm calling opaque orthographies or spellings, and those are ones like those listed, SK2 or 85 degrees, and whatever the third one is, where it's not necessarily easy for either a person or a computer to figure out the pronunciation. Often these are foreign words or novel words and names. So another example would be like the Pontiac Le Mans, which now that we've been here, we can call Le Mans. And so that's another example that sociolinguistic variety, whether someone is a first or second language speaker, whether somebody comes from one place or another, all these things contribute to what you could call non-homophonous homographs, that is, words that are spelled the same, but could be pronounced in multiple ways. So our goal is to learn the pronunciation of out-of-vocabulary words in a pronunciation dictionary system. So traditionally, this problem has been approached with what you could call human pronunciation, such as is exhibited in something like CMU Dict or published dictionaries like Merriam-Webster or Oxford. And then you could learn pronunciations from something like CMU Dict, as we did with tools like Sequitur G2P with a grapheme to phone system that's trained on a dictionary. And what we developed here, we're calling A to P, acoustics to phone. And so we're trying to learn pronunciation directly from acoustic exemplars without reference necessarily to the orthography. And thereby we're trying to capture both interpersonal or sociolinguistic variation and the range of pronunciations associated with a particular spelling. And we're hoping to develop or build the technique or adapt it to systems that use subword units, as many do today, in the future. So our data preparation involved using the Vox Populi data set of European parliamentary proceedings, just the English portion, which interestingly enough included both first and second language speakers of English. We converted the CMU Dict to the International Phonetic Alphabet, and then we found out-of-vocabulary words in the Vox Populi with respect to CMU Dict. And among those words, we selected one for intensive experimentation, just as an example, and then we hope to build from there. The one we chose was Ashraf, as in Camp Ashraf. The reason we chose it is because we did assume that most problematic words today would be named, so this would be an example of that. And this particular word, British might say Ashraf, or Americans or second language speakers might say Ashraf. So already it offers some possibilities of pronunciation variation. However, in the future, we'd like to expand to other more opaque orthographies, and a wider number, of course, so that we can explore the advantages or relationships between A2P and G2P. So the input to our A2P system were GMM likelihoods associated with an HMM system. So what we see, we can visualize that with a phonetic likelihood gram, which is inspired by the phonetic posterior gram, which Sanjeev said had been invented at a prior JSALT. And on the y-axis, we see the phonemes. They're very small. And then on the x-axis, we see a time frame. So this particular one happens to be part of a word yeah, and you can see a lot of activity, for example, in the E and yeah areas. Of course, this was used or was interpreted as an FST, as my colleague Miona will describe.
Thank you, Corey. Okay, so yeah, I'm going to explain kind of how we produce these pronunciations with this composition. So this is basically a composition of, you know, a lexicon-based acoustic model. So we have these 4 components. The first is Y, which is the phoneme sequence. You could see it right here. And this just kind of captures the word hi, and it's based speaker to speaker, how long they spend on each, how long they say a word, basically. And then the next is H, which is the label topology, and that can be seen right here, and that's within each phoneme, so allowing a phoneme to either last one time step or multiple times through this self loop. The next, which is arguably the most important in this project, is the lexicon, or the L, and that's pictured with this huge FST right here. So this is actually the portrayal of Ashraf. We're giving it the amount of states that, you know, we predict the OOV, the given OOV would last, and then all the arcs are all the 40 through 44 phonemes in the English language. So we're basically allowing any possible path or pronunciation to be produced. And then the last is the grammar, which is right here, and that was just provided by the Vox Populi transcripts. And so we took the composition of all 4 components, so you could see GLHY, and then using OpenFST Julia in the spirit of the rest of our team, we use these specific functions, you can see over here, to produce our pronunciations. So these were the pronunciations we got. In this table on the right, so this portrays 10 utterances in the Vox Populi dataset with Ashraf. On the left is the human pronunciations, which were done by Corey. So he actually listened to each utterance and transcribed in IPA what he heard. And then on the right is what our A2P output was. So in 2 particular ones that we found interesting were usually when speakers talk fast, you know, they tend to leave off the last part of the word. So this particular speaker left off the f sound in Ashraf, and both Corey and actually our A2P were able to catch that over here, so you can see that's off. And then also another utterance, Corey heard Ashraf, whereas our A2P found Ashraf, which I guess represented in our FSTs on the right. We kind of got what we wanted, where the A2P is producing a much more diverse set of pronunciations, ones that maybe even humans won't be able to think of. And so some more results based on that. In this table at the top, you can see, so this is our CMU IPA dictionary, and then all these 3 are the dictionary with the added human pronunciations of Ashraf, G2P pronunciations, and our A2P pronunciations. So although you can see that the word error rate between G2P and A2P did go up, what we wanted to kind of bring your attention to is that the recall, in fact, also went up, which is good, meaning that more Ashrafs were recalled. So as like over here on the right, you can see in the human and G2P, there were 3 confusion pairs between Ashraf and another word, whereas A2P, there was only 2, and even more so, one of the confusion pairs was Ashrafs and Ashraf, which is a lot more linguistically digestible than the human and G2P one, where Ashrafs and assets were confused. And that's kind of what these bottom 2 boxes show as well. So while, you know, the word error rate did go up, we do see a lot of benefits of A2P in that linguistically these confusions make a lot more sense to us. And in the future, we're hoping, now that we have this pipeline built, do our experiment on all the other OOVs present, and see what A2P can do. So now I'm going to pass it off to Alessio to show you the second use case.
Thank you. Yeah, so together with Alberto, we'll bring you to the coffee break, going through the second use case that we developed to show try to assess the potential and the needs for the tools that have been developed in the workshop. So this is the slide that Lucas showed at the very beginning of the presentation to motivate the need for efficient, modular, flexible tools for modern ASR. And this is actually how currently speech services work, so are provided. So you have a variety of different devices, all accessing speech services on a central system. And this centralized solution currently works. Everybody uses the speech services, but there are some issues that are getting more evident as we use the services. There are problems related to privacy because you have to send your data to some clouds located somewhere. And also there are issues related to the energy and the bandwidth that you need in order to transfer the data back and forth. And energy is getting quite expensive today. So if you try to save energy, it's better. So there is this Edge Cloud Computing Continuum is an emerging framework where you can deploy the processes in the different nodes of the infrastructure. And of course, in this case, we are interested in the No, okay, I give up. On the edge nodes, so the devices where the data are produced. So if you can process the data there, then you handle the problems related to privacy, energy, and bandwidth because the data never leave the device, or they don't always go up to the cloud. Okay, so this is a very, very interesting from this point of view. On the other hand, doing the processing on the edge devices, you have other problems, and in particular, the computational resources, the computational budget that you have on the devices is typically limited. It is time varying because your mobile phone has to do other things, not just let you play with the speech recognition. And then different devices may have very different computational budgets. So in the previous slide, there was a server, a car, a mobile phone. So there are solutions in literature. I mean, everybody, I'm sure, is aware of this. There are solutions to reduce the complexity of neural models in order to fit some requirements in terms of computational budget, pruning, student-teacher, and so on and so forth. The limitation of these methods is that they are static, and so they're not suitable for our time-varying scenario. Okay. Of course, I can have 1,000 different models with different requirements and select the best one every time, but that is not very practical. So what we are looking for are dynamic models in order to change the behavior of the model depending on what device it is running on and what are the current resources available on the device. And there are these early exit architectures are very interesting from this point of view because basically they introduce intermediate branches where you can exit and you don't have to go through the whole model in order to get your prediction or your result. So what you can do, you can condition the processing based on the resources. I can afford 4 layers. I exit after 4 layers and whatever I have. Or you can condition the processing on the results. After 6 layers, my result will be as good as going up to the end, so I can stop here and save energy, save budget. And also, this is something that we didn't investigate in the workshop for lack of time. But they are also useful if you do federated learning on heterogeneous models that would fit heterogeneous devices. Okay, because they have this modular structure. So early exit architecture are being investigated in literature. There are some work coming out about this, in particular focusing on the inference part. So what we wanted to do in the workshop was to explore locally normalized and globally normalized losses, so CTC basically and MMI, to train these early exit architectures. And if training the model with the early exit models with CTC is quite, let's say, straightforward, you combine the losses and it works. When you use MMI and you have the denominator lattices, then it's a little bit more tricky. It's not so straightforward. So now I leave the floor to Umberto, who actually did the actual job, and tell us about the training.
Okay, so hello everybody. I'm Umberto. So I'm going to talk about the experiment we carry out for our early exit experiments. So I would like to start with some basic implementation details. So as Alessio told, we have trained an ASR system using CTC or MMI criteria. And we have used a conformer model with 12 layers as our backbone model. And we have inserted an exit layer every 2 layers, basically. So we have in total 6 exits. During training, we basically compute these 6 losses. We sum them up, and then we minimize their combination. In inference, instead, we need to decide based on some criteria when to exit, and this will be tackled by Alessio later on. An important remark here is that for all our experiments, we have used IceFall, K2, and we have tested all the experiments on LibreSpeech 100. So now, in this plot, we can see the trend of the word error rate as a function of the exit layer ID, both for MMI and for CTC. Well, for MMI, we can see that we get very interesting results even after just 2 layers, whereas for CTC, the performance are pretty bad. But as we proceed through the network, we see that CTC overtakes the MMI criterion. So I would like to have a look here at the last exit. So basically, the points here are our baselines without early exit. So we can see that by using the early exit approach, we can improve the word error rate for the last layer. But we can also see that if we decide to go through, we decide to exit in the middle of the network, we can see that for MMI we get the same result as the baseline, and for CTC we even improve a bit the performance. But in practice we have reduced the compute budget by half. So in line with what I've just said, we have tried to compare our model with 12 layers with early exit with a setting in which we have 3 different models with 2, 6, and 12 layers. We train them without early exit, and we compare with our early exit model with 2, 6 when we exit at 2, 6, or 12 layers. So we can see that if we decide to exit after 2 layers, the non-early exit approach is better, so the model trained with just 2 layers is superior. By the way, when we decide to exit in the middle or at the very last layer, we see that early exit is efficient and achieves the best results. Also, you know, if you have 3 models, it is more difficult to maintain all of them. Whereas with one single model with early exit, this is easier. So then now we have found some issues for MMI and CTC. For example, MMI is pretty expensive to compute. So in practical application, computing 5 additional losses can be quite prohibitive. Another weak point is that we don't see a very huge increase after the 8th layer. So we basically have a kind of plateau in the performance. So we try to come up with we come up with an idea where we try to compute a single, so we dispense with the computation of these intermediate losses, but we sum the intermediate output representation from the exit, and on top of that we compute the MMI loss. So basically we have just one term. And this can be seen as a sort of intersection of the intermediate lattices. Okay, so basically the performance is not very well. I mean, we get a slight improvement for the last 2 layers, but unfortunately for the when we proceed backwards into the network, the performance are not very nice. And here we speculate that the wrong assumption was that if we decide to compute the FST on the sum of the output, this is not equivalent to computing the FST on the single early exit and then sum them. Then for CTC we have an opposite trend, because the issue is at the very beginning of the network, because the first exit brings poor performance. So in order to improve this performance, we try to exploit the self-knowledge distillation technique. So basically we use the last layer, which brings good performance, good results, as teacher for the 2 first exit layers, in order to promote transfer knowledge. We have investigated 2 different directions. One, I call it feature space feature space KD, because basically after we get the auto representation from our conformal blocks from the student, and this is the teacher, and we compute basically a knowledge distillation loss here. This is a cosine similarity. Another possibility is to go through also the exit layers. We basically have a distribution over the tokens for each frame, and we compute also here a knowledge distillation. So we have explored these two different strategies. So for prediction space KD, we observe some marginal uniform improvements over all the exit, basically. Whereas it is more interesting for the feature space KD because we get interesting improvements in the word error rate for these two exit layers, and we basically have applied the two knowledge distillation losses to these two layers. But it seems like also the other layers benefit from this technique. Okay, so now I hand it over to Alessio for the inference part.
Thank you. Okay, so to complement the experiment of Umberto, we did also an analysis in inference comparing the behavior of the two models, trained with the two strategies. And so the current state of the art in inference, when you want to select the exit, the best exit is to use the frame-based entropy as a measure of the quality of the output. So we try to compare the models using an oracle selection. So we take the first exit with the lowest word error rate, an entropy-based selection where you compute the entropy across all the outputs. This is not practical because if you have to compute all the outputs, then we take the last one. But it gives some interesting insight, I think. And then the classical approach, which is a thresholding. So basically you define a threshold, and then you stop at the first exit whose entropy is below the threshold. And the threshold determines how much budget you want to use. Okay, so these are the results. The first two histograms on top show the distribution of the exits using the oracle selection. So it is interesting, in my opinion, to observe that for the MMI model, which is on the right, the most frequent exit is the first one. This is in line with what Umberto observed. MMI helps a lot in the first layers. On the other hand, the CTC model, you see that the distribution is a little bit more shift on the right. Okay, so these are preliminary experiments on LibreSpeech 100, but I think these trends are clear. And also in terms of oracle word error rate, the MMI model would be a little bit better than the CTC one. Unfortunately, when you use the entropy to select the exit, while the CTC, at least behave as the last layer with a little bit of computation reduction, the MMI case, the word error rate deteriorates. And I think this is reasonable because CTC basically minimizes the entropy, MMI maybe not directly the entropy. So it could be, it makes sense. And also if you consider the classical approach, the thresholding. So here in this figure you have the average exit and the word error rate for different thresholds. Okay, so if you change the threshold, you move along the curves. And so very low thresholds, you are on the bottom right. Very high threshold, you are on the top left. The other way around. So you see that again, if you have a threshold that if you want to use a very low computational budget, the MMI model is better. That those thresholds are better. Those thresholds in that area. No, whatever. I gave up. Are better, but on the upper part, the CTC is better. So this is in line also with what Umberto observed, but also doing the inference experiments confirm the trend. So to wrap up, I would like to say that MMI has potential, apparently, to provide better trade-offs in terms of performance and inference in this application scenario. But the combination intersection of I would say the denominator lattices is still a little bit tricky, and we have to further investigate on that. And also for the inference part, entropy, which is what is currently used in literature, is not a good option. We have probably to investigate lattice-based exit selection. So basically, we need efficient linear algebra tools to manipulate the lattices. So I'm very eager to use the tool developed by our colleagues. And let me also spend 10 seconds to say that federated learning, we didn't work directly here, but we did work on that using the early exit architecture with heterogeneous models on heterogeneous nodes. And we have some preliminary interesting results. So apparently, the model learns, even if the client models are heterogeneous. And my colleague Mohamed also developed an integration between Flower, which is a tool for federated learning, and K2 Icefall. It is available in that repository, GitHub repository. And so this is something that we're going to explore we're going to use to further explore in this direction. So to conclude, well, first of all, I wanted to say hello to my kids and my wife. They're watching on YouTube. Ciao, ci vediamo domani. And then we can go to the break unless you have questions. Otherwise, we can go to the break.
No question from online, maybe, or no?
I had a comment, not a question. A quick, if you go back to the slide where Umberto had the conclusion for the failed experiment, I think our conclusion, yeah, further back. Yeah, it's a wrong assumption. I think the assumption is not that the sum of the outputs is I guess it depends on what you mean by the output, because the FST part is correct. What happens is when you compute the MMI loss, the MMI loss of the sum is not the sum of the MMI losses or whatever losses you compute. So then when you compute the gradients, that's where the assumption fails, yeah.
From a FSP perspective, we were trying to approximate the union with some kind of intersection. We're hoping that it will be close enough because the gradient should be kind of okay. But unfortunately, it turned out to be not true for the very early stages.
I have a general question. Is the FSD suitable for all types of sequence-to-sequence tasks?
Yes. So I mean, they are kind of designed to process sequences. So they are naturally fit for sequence, and they are function on sequences. So my yes is not so crazy in a sense. Yes, they are for this. Maybe the limitation of finite state transducer is they are finite. So for instance, if you're thinking about making a FST BERT, ChatGPT, sorry, that's maybe a little bit hard because here you require the context which is near infinite, and here the finite state transducer framework won't be that powerful. So I want to just, so let me make the following, to rephrase my answer. I think finite state transducer are great for speech because for most of the application, we don't need infinite context. I mean, these are very special cases. And there we can do sequence-to-sequence processing extremely efficiently with a great control. And they allow us, again, to bring control about what we want, if we want to input the knowledge into the system and everything. So they are for sequence-to-sequence processing with the limitation that they have finite state or finite context.
One more.
My question is for the phonetic part, actually. So I'm wondering if you try to compare to graphemic without any phonetization, the word error rate, because for multiple languages we don't have a solution to get phonetic form, actually. So did you compare to just train a LSR system with graphemic representation?
No, we haven't, but that would be a good idea for our follow-up work. Yeah.
More questions? Okay, thanks everyone for coming to our last session. Probabilistic modeling of microphone. I'm not loud enough? No, for the online. Okay. Your voice doesn't reach New York. Perfect. Thanks everyone for coming to our last session, Probabilistic Modeling of Modern ASR. I'm Ehsan, and I'm presenting a work of our team from Google, and also all the participants in JSALT. So, from the movement of acoustic modeling from GMM to deep neural networks, we saw a lot of gains on order rate, which a lot of them was attributed to better toolings and better engineerings, and of course simplification of tools and pipelines for ASR E2E training. But this progress was not for free. There was some costs. Some of the major costs was we eventually moved away from probabilistic modeling to black box formulation. And of course, this came with lack of controllability and explainability, and introduced a lot of many new open problems like streaming, language model integration, and so on. Our research team in Google is to develop a probabilistic formulation for model neuron ASR that can be used to address these problems. So last, lattice-based speech transducer is basically the formulation that we think has that ability. So it's a differentiable weighted finite state automata framework. It's modular. It has 3 components: context dependency, alignment lattice, and weight function, which I'm going to describe a little bit in next page. And with these, you can basically formulate any existing training criteria in ASR. So it's universal. And if you'd like to learn more about them, please read our papers, our Norwich paper or our ICAS paper cited here. Okay, so what is LAST? So as I mentioned, LAST has multiple components, and that's how it is. And that's why it is modular. The first component is what we call context dependency. What you see on the left top. Context dependency is basically a WFSA that accepts any language, any sequence from your alphabet. So imagine you have a 2-letter alphabet A and B. The n-gram context dependency for n equal 1 in this figure is basically accepting any sequence that you can make from A and B, right? So starting from the initial state, okay, I should do it this way. Yeah. Starting from the initial state, you can basically take the transitions and produce basically any sequence of A and B. So this is basically enough to model the label side of things, but you also need to model the acoustic side of things. And that's what we have, alignment lattice, which is shown on the top right figure B here. So imagine you have 3 frames, x1, x2, x3, and you make an assumption that at each frame you almost emit 1 label. So you either have a label or an epsilon. So what you see here is basically alignment lattice that supports this assumption. We call it frame-dependent alignment lattice. If you intersect these 2 acceptors, you will make something that we call recognition lattice, which you see on the bottom. So the recognition lattice, as you see, is corresponding to 3 frames: frame 1, frame 2, frame 3. And basically, every path here is an alignment between these 3 frames and the label sequences. I mean, our ultimate goal for using this model is basically to assign probabilities to different alignments. So we need to assign weights to each of these transitions. So here I'm showing the recognition lattice again with weights. So as you see, each state has basically 3 outgoing arc, and between each time frame we have 9 weights. So for sample path AB epsilon, which is basically the highlighted path here, the way we assign probability to this path is this equation here. On the numerator, you see basically the path score, which is basically exponential of sum of the weights. So first arc is W02, second arc is W16, and the last arc is W27. And what you see in the denominator is sum of all the possible paths. Okay, so this structure that this recognition lattice basically induce allows us to have efficient algorithms for shortest distance on accelerators for both training and inference. Training will be just sum over all the paths, and inference will be basically finding the most likely path, which is a max. During the talk, you will hear a lot about local versus global normalization. So high-level definition, local normalization and global normalization are different on how they constrain these weights on this recognition lattice. For locally normalized, the weights are a logarithmic of distribution. So basically, they are all less than 0, and the exponential of sum of exponentials will be 1. For the global normalization, on the other hand, there is no constraint. So basically, they can take any value in real domain. So as I said, one feature of LAST is that like it's a universal formulation. So it can already explain all the existing models, including cross entropy, CTC, RNT, LAHAT, LAS. And basically here, I'm showing that like each of these models are basically different configuration of these components. And if you'd like to learn more, please read the appendix of our Norwich paper. So we made this formulation mainly to basically be able to diagnose the issues, the problems with the ASR problem, with the ASR models, and solve them one by one. So, for example, we published a GNAT paper in 2022, which looks at the streaming problem, and it compares basically, it argues that the reason for poor streaming performance is the local normalization of these models. And here you see, like if you switch to global normalization, you basically can get huge gain across many tasks, like common voice, switch, Bertelium, and so on. We also have looked at lattice entropy, time alignment, and beam search. So with this background, we came to the JSALT to solve more problems. The first problem we have been working on is software. So LAST comes with a JAX-based software. It's open sourced under GitHub here. And the main design objectives are easy to use, scalable, and accelerator friendly. And basically, our ultimate goal is anyone with any background can train a state-of-the-art ASR model using LAST. So the first problem we brought to JSALT was basically having LAST in PyTorch. And the reason is a lot of people in the community are not using JAX, but they're using PyTorch. So it makes sense to have same software in PyTorch so that everyone can use it. The second problem we brought to JSALT is long form. If the lattice gets longer, meaning if you have longer sequences, it's harder to process for both training and decoding. And of course, you have a lot of mismatches between training and decoding because usually training is done on shorter segments, decoding is done on longer segments. So this mismatch is basically difficult to handle. And for our second problem, we wanted to look on how to address this long form problem using global normalization. Our third problem is metrics. Again, I'm showing the recognition lattice with two paths highlighted here. The path on the bottom is AB epsilon. And this path basically is the true alignment path, meaning like at time frame 1, A happened, and then at time frame 2, B happened, at time frame 3, epsilon happened. But at the same time, it's possible that in this specific lattice, the most likely path, the path with the highest score, be epsilon AB, which is basically the path highlighted above. This thing doesn't work. Okay, yeah, epsilon AB. The current metric we have in ASR, which is order rate, does not make any distinction between these two paths and assigns 0 order rate. But at the same time, we know for many applications, streaming matters and like voice search. So we need a metric that basically include these differences. So that's our third problem, a streaming order rate to our metric. Okay. Our fourth problem is beam search and global normalization. Global, as I mentioned earlier, globally normalized models basically have no constraints on the weights. So the weights can take any values from -infinity to +infinity. So here in this figure, I subtracted m from one edge and distributed that m to all the other edge, leaving the immediate next state. And for any value of m, this lattice will assign same distribution on all the paths. So it doesn't change the distribution of the paths. You can imagine this is a very big problem if you do like beam search. Just think about it like you do beam search with a beam size of 1. And the best path starts with the 0 epsilon to 1a. You can easily miss it if that one is -infinity. So Our next problem, problem 4, was how we can make beam search work for global normalization. And finally, our 5th problem is the speech representation. So ASR is useful in many tasks these days. It's an upstream for many pipelines and with many downstream tasks like voice search, machine translation, or intent classification. The common approach right now is Cascade, which is basically getting one best output of ASR and pass it to the downstream. The benefit of this task, paradigm of Cascade pipelines is that it's portable, meaning you change your upstream ASR. You don't necessarily need to retrain everything downstream. But at the same time, it's not the best you can do because you have information loss. ASR is not perfect. The error propagates to the, from upstream propagates to the downstream, and you have disjoint optimization. So in this problem, we ask if we can do better. So we are looking for a representation that is accelerator friendly. It is differentiable. So let's say your task is machine translation. You want to translate English speech to French text. And imagine you have pairwise data of like English speech, English text, and French text. We want to have a representation that basically can be trained from very back end of downstream task to the very beginning of upstream task. We also want it to be portable, meaning if we somehow change the upstream task, like for example, we improve ASR, we don't necessarily need to retrain everything on the downstream. And with that, I will pass it to Imani to talk about software.
Hello, good afternoon. I'm Imani, and I will be talking about software, and surprise, surprise, there is a GitHub for this. Okay. So just to go back and talk about LAST. LAST, again, is a JAX library for building lattice-based speech transducer models. That is the GitHub link right there, as promised. And the main thing that I want to highlight about LAST, just in the dialogue that we're talking about within WFSTs, is that it does implement these differentiable WFSA algorithms so that you can present a lattice that models speech as now probabilistic hypotheses rather than text that you would find in traditional end-to-end models. And so the main components or modules of LAST is following along with the Ganat paper, and that is context dependency, which encodes our output history, alignment lattice, which encodes the correspondence between the input frames and the output labels, weight function, and then the recognition lattice, which is pictured on the right, and you have seen and will see again throughout this presentation. And so what we present to you today is PyLast, which is now the PyTorch library for building lattice-based speech transducer models. And it is literally just converting that JAX API into a PyTorch one for the sake of PyTorch being a more familiar ML framework with comparable functionality with JAX in the sense specifically that you're able to create customizable gradient functions, and it has that neural network module. And the current status of that library is that we are at 95% completion, happily. And yeah, I will show a demo of how to use LAST, though, because they are very similar in their implementation. Now, how do I do that? Okay, wait, no, wait, I did it?
You get it? All right.
I think. Okay. Sure. How do I make it big? Yeah.
Like this?
Yeah, that's perfect. Awesome. Thank you. Okay, yes. So this is just a quick demo into just demonstrating a glimpse of how to utilize the LAST API and therefore how you would utilize the PyLast API once it is released. So yeah, we will be going over how to build just a simple speech recognition model using LAST. And we are training and evaluating using the Jakubowski free spoken digit dataset. So I will skip over the installation and just a little bit brief on the JAX ecosystem. JAX is not like a complete ML like toolkit, so there's also the extension of FLAX, which is basically like Torch EndtoEnd, so the neural network model, and then Optax, which is like for optimization, though we won't really be touching upon that in this demo. And we are using TensorFlow datasets to load data. So the example task that we are using is just a spoken digit classification, and the goal is to train the model to spell out the letters of each number. So it hears 2, spell out 2. let's go down. So here are some spectrograms of kind of like the audio that it will be receiving. And so we will be evaluating on a single batch from the first 1,000 examples, and then training on the rest of that data. And just a note that we are operating in NumPy arrays because that's just how JAX operates. And so yeah, so for our simple speech recognition model, we are using a unidirectional LSTM encoder, thus it's a streaming. And we're also using a decoder that is then built by the last recognition module, which is trained via GNAT. So what I really want to emphasize here for the encoder, even though it's just a very traditional and simple LSTM encoder, is that we are using Flax's NN optimized LSTM cell, and then the, oh, I have a pointer. That works, yes. With the functions, the initialize carry, which returns the hidden state of the LSTM, and then call, which returns a new hidden state after a single input. And then I won't really talk about scan, but those two are very important in building the encoder, which you can get a glimpse of in the code that follows, though we won't be examining it in great detail. What I really want to focus on specifically is actually using the last recognition lattice module, which again uses that context dependency, alignment lattice, and weight function to create our decoder. Sorry, let me scroll back up. So our model is providing two functionalities: call, which computes the loss value, and decode, which decodes a batch, returning the hypotheses of the alignment labels. And we are scrolling down to this section in particular, which actually calls the last recognition lattice library, or module, I should say, and is building a full n-gram context dependency with a frame-dependent alignment lattice. And yeah, you can learn more about this in the GitHub. And yeah, let me scroll past. And so the example that we are looking at is basically we're training two models, and one locally normalized and one globally normalized, and we're comparing the effects of the two. Okay. And so what I will highlight for this in particular is just the respective losses. How do I scroll to the side? So the training loss and then the accuracy. Yeah. So this is for the locally normalized model, and you can see, like, I'll just choose these two pairs down here. So this is 0.22, and then the training loss is 0.0016. And then when we look at the same for the globally normalized, scroll over, this is, whoa, 0.05, and this is 0.003. So we just see that this is just to exemplify what GNAT talked about in their paper, in that global normalization, compared to local normalization, you would observe that local normalization just overfits, and they're just, global normalized just improves upon for loss. And yeah, that is the conclusion of my demo. Go back to here. Okay, cool. Okay, so in conclusion, PyLast is a software package that implements WFSTs for richer speech representation within ASR models. The future work that we will be moving forward with is completing that remaining 5%, of course, and also addressing the limitations within this first version, in that this version was created definitely as a PyTorch conversion from JAX rather than a standalone PyTorch library. So there's a lot of the current API that is catered towards matching what JAX did in the original version rather than truly utilizing the capabilities of Torch as it is. And of course, we have to do benchmark analysis and then officially release that public package and API so that you guys can have access to that GitHub you're so waiting for, and as well as publish a paper. So just keep an eye out for PyLast, and yeah, that is it. I'm gonna hand it off to...
Wait, there is a question online from Michael.
Okay.
I think you already more or less replied. Okay. I cannot mimic his voice, so I just read. So, what remains to be done for PyLast, and will there be a collab similar to the JAX one you just presented?
Yes, there will be a collab, and what remains is just finishing up the last of the recognition lattice module. So thank you for your question. Okay. Now I'm handing it off to long form. All right.
So I'm going to be talking about the second problem from Eson's long list of problems that we're looking at here, which is long-form speech processing. Awesome. So long-form speech processing is difficult, both because it's just a difficult research question, but we think especially because it's something that just hasn't been explored that much and is definitely not reflected in the typical research corpora that we see for these types of problems. So we're going to be looking at both speech recognition and speech translation. And in both of those cases, typically what we see are data sets that come pre-segmented, both for training and for inference. So typically, or at least often, these are segmented based on qualities of the reference text that you don't actually have at inference time in a real-world setting. And this means often that the audio has been trimmed to exclude things like silence and non-speech, and we tend to have just single speaker segments. And as I said, this is in contrast to the type of audio that we're actually trying to transcribe or translate in real-world scenarios. So you can think about a whole podcast or a lecture or a meeting recording, something like that. It doesn't come with any pre-segmentation. So our goal is to look at how we can build these type of systems to include that segmentation piece as part of the inference process to actually sort of effectively handle long audios at inference time. And within the context of this JSALT project, we're looking specifically at whether these WFST-based models can help us improve performance in this long-form inference scenario. So as I said, we'll be looking both at long-form ASR and also at speech translation. So the sort of first thing we need if we're going to do research on this problem is to figure out what data we're going to use. Typically in the research literature, the most common thing you'll see for people who do study this long-form problem is basically simulated long-form data created by concatenating existing segments together. We think this is not ideal because it definitely doesn't reflect that real-world long-form audio. So as I said, if the original audio has been trimmed to exclude things like non-speech or silence, that's not going to be included in this concatenated audio. And the concatenated audio also has the problem of these sort of discontinuities in the signal that can cause problems for the model and aren't reflective of what the model actually needs to be able to handle in real-world scenarios. Our group has released a couple of data sets of real long-form audio in the form of public company earnings calls. The issue with this in terms of experiments for JSALT is that these data sets are evaluation only, so there's still no training data of this form available. So now I will pass it off to Corey, who will talk about the data work we did.
Thank you, Jenny. So we identified a few proto-long-form corpora. In their state as they were delivered, they might not be well suited to the problem, but there were some adaptations that we undertook to make them more usable in this context. So one of the minimal requirements is that there's full audio. There are recordings of an entire TED Talk, an entire parliamentary session, rather than the little bits and pieces that they also give you. Also, we want some segments, since they do give you small segments or small start and end times, that we could link some of those together to form larger segments. So the three corpora we used were GigaSpeech, Tedlium, built here, and Vox Populi's English segment. So the process that we undertook we call reconstitution, putting back together again. Some of the things that we need to do are to fill in missing transcriptions. This enables both linking, as you'll see, and possibly the expansion of the corpora to include more transcriptions than were in the original training set. The easiest way to fill in transcriptions was offered by Vox Populi, because Vox Populi had a large number of segments, more than half, that they identified as invalid based on having run it on ASR and it didn't do so well, so they said, let's move on. So we resuscitated those, as you'll see. And also the next level would be something like Tedlium, which good as it is, early on we noticed there were certain things that people were saying that were not included in the transcripts. So Desh recommended we look at the TED scrape, which had the full transcripts. And so that was the way that we were able to fill in transcripts from another source. And then the hardest would be GigaSpeech, which we haven't done, and that would be, we know where the untranscribed segments are, but they're not available to find, download, etc. So we would need to send them to a place like Rev or other to get them transcribed. The linking, once you know, well, in the case of GigaSpeech, it was pretty easy. They had like segment 25, then segment 27, and there was a gap in between, so we knew that we couldn't link 25 to 27, but 27 and 28 were directly contiguous, so they could be. And sometimes there's a little bit, a word might be cut off in between, so when you actually remove the boundary between two segments, you actually get a more interpretable signal. And then in the case of Tedlium, we could do two things, and the first we've already done, and that is we've identified where the missing transcriptions are, so we've linked everything that doesn't have one of those in between, but we haven't yet incorporated those missing transcriptions to create new segments or to add to the database. And finally, when we do create new longer segments, we need to force align them to get the word timings, and we've been using Meta's Wave-to-Vec aligner for that. So here's an example from Tedlium. The top is Tedlium as you download it. So you see that something that was in one segment and become very important, there's not very much time in between, about 0.0 seconds, and sure enough, when you actually look at the full TED scrape, you see there was nothing in between. So that's kind of a license to link those two. However, in another case, when there's also a small gap between 124.96 and 125.55, inspired by Unc of Fact, we see when we consult the missing transcriptions that there was a couple words in between. So we couldn't link those until we fill in those transcriptions. Vox Populi, as I mentioned, had over 50% labeled invalid. That was based on some recognition that was done. Some of the challenges I think they encountered at that time were the L2 speakers and also non-verbatim transcriptions. So I guess somebody was told to prettify when sort of or L2 grammar, as well as add niceties like Mr. President and things like that into the transcript where people didn't say those things. The first thing we have done is we combine segments at the paragraph level. A paragraph is like a monologue of one speaker. But the next thing we'd like to do is to go higher into the session level so there would be multiple speakers. So saving more data means that there's a lot of data in Tedlium, or there's a lot of data in Vox Populi. Some of it just wasn't put in the training partition. Nor the test or dev partitions, but it's there. And so that's what we mean by saving data. And as we run the aligner, we can identify segments that may not be well aligned due to some of the transcription problems. So that would be someone's option to still not use particular ones. So this is a chart of the reconstituted data, and we've put it in our GitHub where we have earnings 21 and earnings 22. Jenny's added some of the work we've done this summer, and there will be more added. So as you can see, GigaSpeech got a little bigger when we did this linking. There were no new transcriptions added, but the linking by kind of resuscitating some of the silence or noise in between some of the segments they had originally delivered did result in a slightly longer corpus overall, and also a much larger average segment length. And then Tedlium, we increased slightly, but could increase more as we add transcriptions. And the segment length, as you see, increased dramatically. Vox Populi, I think, is the most dramatic, where the database will double, and then the average segment length will also increase. And so now I'm going to pass it back to Jenny to talk about some of the experiments that we ran.
Those are seconds. Yep. Thank you. Okay, so now that we have our data, we can actually do some experiments. So these graphs come from a 2022 paper. So this is some prior work that's been done on long-form ASR. And you can see on the left, this is using concatenated segments, like a lot of research papers do. But the left-hand side is looking at holding the training constant and increasing the length of the test segments by concatenating more and more utterances together. And then on the right side, we have holding the length of the test segments constant, but looking at training on longer and longer segments. So something that we wanted to do with our new data was first kind of replicate these experiments and just see that these results are reflected on this real world data that we've developed, but then also do sort of a bit more in terms of looking at the interaction between segmentation at training and test. So not just holding either train or test fixed, but looking at how those sort of correspond to each other. And then additionally, this paper looked at RNNT models, but we wanted to look at that RNNT, which seems to be sort of the most popular loss function now, but compare it to this globally normalized MMI model. So Esson showed some results on streaming earlier about how the globally normalized models really help with the sort of domain match between standard ASR training and streaming recognition. And so our hypothesis is that globally normalized models will also help in this case with the sort of domain mismatch between training on short segments and then doing inference on longer segments. So that's what we wanted to explore here. For data, the results that I'll show are just on GigaSpeech. That was sort of the first data set that we had prepared for the summer. And I looked at 3 different subsets of it. So I started with the medium subset, which is one of the standard splits available in the GigaSpeech corpus. And that's around 1,000 hours. And so we just used the original segments as they were released with GigaSpeech. And then we also look at what we call long form version of the medium subset. So that's all of the exact same transcriptions that are in the medium subset. But what we've done is basically use these much longer segments that we were able to string together through the linking process that Corey described. And then for training purposes, we can't train on infinitely long segments because there's big memory requirements of our neural network models. So what we do is we take those long segments, but then we basically resegment them down to either a maximum length of 15 or 30 seconds. And then I did a last subset, which is a smaller amount of data. It's only 200 hours, but these were all long segments, which meant that when I resegmented them into either 15 or 30-second segments, now every segment in the training corpus is that 15 or 30-second length. So this is basically training on just fixed long segments as opposed to that second long-form medium set, which has sort of mixed segment lengths. So segment lengths up to 15 seconds versus segment lengths of only 15 seconds. For evaluation, we looked at the GigaSpeech test set as well as earnings 21. And for the GigaSpeech test set, there are some missing segments there as well as there were in the training data. What we did is run inference in this long form scenario where we ingest the entire audio, and then we used the output timestamps to basically remove any ASR hypotheses that occur in between the test references. So that's how we sort of adapted that to the long form use case. When I say that we ingest the full audio for long form ASR, I don't mean that we just take 20 minutes and run it through the model in one shot. Instead, what we do is this pretty standard chunk-wise inference procedure where we just simply split our audio into these fixed length chunks. And we do a little bit of overlap so that we can avoid errors that happen at the boundaries where you cut a word in the middle when you do your chunking. So for the first set of results, this is looking at models trained on that original medium subset. So these are trained on the original short segments without any of the linking that we did. What you can see is that when we use the original test segments for the GigaSpeech test set, the RNNT model is a little bit better than the MMI model, although they're close. But as soon as we go to this long-form decoding scenario, the RNNT model suffers quite a bit, whereas the MMI model is very robust to this switch from the sort of standard original segmentation to these fixed chunks that we use for long-form inference. And then for the earnings data set, we don't have any original segmentation. That's only available as these long transcripts, so there's no original segmentation for comparison there. But again, we see that the RNNT model is significantly worse than the MMI model in that scenario. The next set of results are models trained on that smaller 200-hour subset. So these are models trained on fixed length segments. So the legends here describe the training conditions. So we have the model type, and then we have the segmentation of the training data in the legend. So when it says, again, 15 seconds or 30 seconds there, that means every training segment was either 15 seconds or 30 seconds. So that's sort of our long-form training scenario. So the main thing to take away, the blue lines at the top, again, are the RNNT model trained on the original segmentation. So we see that it really suffers in the long-form inference use case. But once we train on these longer segments that match our inference condition, we get much better performance. But ultimately, the best performance overall, you can see, let's see if I can do this. There we go. So you can see, especially on this side, the MMI model does get a little bit of improvement still from training on the fixed segments rather than the original segmentation. So the best performance overall is the MMI model trained on the long segments. So the, actually I'll go back. The previous page, we see that we can get better performance out of the RNNT model when we train on long segments. But the reality is this is a relatively small subset of our data, and we can't get these long segments out of the full 1,000 hours that we have. And so while the RNNT model gets much closer to the performance of the MMI model, the absolute word error rates on this page are not very good. So it's only trained on 200 hours. So we wanted to look at also training in the non-long form fashion, so just on the original medium model, but then fine-tuning on different long form sets. So the blue line, this is just the earnings 21 data. The blue line is that original medium model, and then we have fine-tuning either on, again, the 200-hour set or the full 1,000 hours with those mixed segment lengths, both short and long. And ultimately what we see, that lowest line is the green line there, and that corresponds to fine-tuning on the 200 hours split into 30-second segments. So it's actually better to fine-tune on less data that's better matched to the inference condition than to fine-tune on the full data set, but that doesn't match as well to the inference condition. So just to wrap up here, what we've seen out of these ASR results is that the MMI model is very robust to this long-form inference condition, as we hypothesized, but that we are able to improve the RNNT model with this long-form training. One thing we noticed in doing these experiments is that the MMI training and inference is pretty memory hungry, especially as we get up to these 30, 45-second long segments. And so this is just to highlight what Alessio said after his experiments as well, that there really is still a need for more efficient algorithms for working with these models. And I too am excited to continue working with the tools that have been developed during this workshop. And this QR code is just another link to our GitHub, which we will be populating with more and more of the data that we developed this summer. So now I will pass it off to Peter, who will talk about speech translation. Yeah.
There's a question from Paula. What can be done when you have around 8 or 9 hours of recordings? She's referring to the long-form RNNT experiment.
Yeah. So I think what this shows is that it depends whether you have really complete transcriptions for those 8 or 9 hours, where you can do your training in a long-form fashion. But I think ultimately what this demonstrates is if you have even a relatively small amount of data that's sort of fully transcribed, where you can get these longer segments out of it, you can effectively fine-tune a better model a model trained on more data specifically for the long form use case.
So just regarding the question, I also wanted to bring some theoretical perspective. So on the problem of segmenting extremely long segments, we didn't mention in the first page, but this again like the shortest distance algorithm for kind of forward backward for decoding, and this we already know that it can be brought down to a logarithmic space complexity. So in a sense, we can deal with the long memory explosion at the expense of relatively better, more computation, but we saw that things can be parallelized. So theoretically speaking, again, like FST can deal with insanely long segments because we just make the complexity logarithmic.
Was that it? Okay.
So hello everyone, my name is Peter. And I'll be talking about long-form streaming speech translation. So, as Jenny said, the way how we deal with the long-form audio is usually that we split it into fixed-size segments, and then we do the inference on them. But the thing is that in case of speech translation, the things are getting more difficult because unlike speech recognition, speech translation, like the translation task, contains generally some kind of reordering. Like here we have an example in English to German. So there's no monotonic alignment, or like we cannot expect the monotonic alignment between the source speech and the target translation. Another issue in SST is that most of the research, actually basically all of it, somehow expects that the data sets come pre-segmented into nice sentences, so the models are just not robust. So all in all, SST is very sensitive to bad segmentation because because of the training, and second, because of the inherent problem with the translation. And so we thought, how can we use the FSTs to help us to solve this problem? How can we get better segmentations? So what we want to do is to segment it on sentence level. The thing is that here's an example. So we have English speech and German translation, and the colors here denote the alignment. And so in these experiments, we are using CTC alignment between the source English speech and the German translation. And if you look closely, you can see that the alignment isn't necessarily perfect on the subword level. But what's important is the punctuation alignment, which appears to be quite good. So if we know where the punctuation appears, we know where to segment. And our preliminary results indicate the results are pretty good. So we already are matching the state-of-the-art offline segmentation methods, but less surprisingly, we still underperform Oracle, but I guess that will be never possible. But this is just ongoing work, so we'll work on it and hopefully report the results later. Thank you. I'll pass the mic to Desh, who will talk about chunk-wise again for ASR.
Thank you, Peter. All right, so Jenny showed you this slide earlier, and this basically talks about chunk-wise inference that we perform for long-form ASR. And the idea here, again, is that if you go into recordings that are several minutes or up to several hours, it becomes harder to create these lattices, which we want to do because we know that lattices are good, WFSTs are good. So what we do instead is we break down this long recording into fixed size chunks, and we want to build lattices or get lattices for each of these chunks. And this is kind of easy if you think about models, finite context models like CTC, which is shown here on the left. So for a CTC model, for example, the outputs can be naturally interpreted as a dense FST, and you can then compose it with a kind of alignment lattice that, again, Hassan talked about earlier, to get a recognition lattice. So on the right here, you see a natural CTC lattice, which is usually denoted as TFST. And the composition of this gives you a recognition lattice. But this kind of thing is hard to do for transducers. And this is because of two reasons. The first is that in general, when we work with RNN transducers, the prediction network usually consists of LSTM layers. And LSTM layers have infinite context. The second reason is that in general, when we train these RNN transducers, the lattice looks something like this. So we have T on the horizontal axis, U on the vertical axis, denoting the label sequence. And we are allowed any possible alignment. So we are allowed to have any number of tokens emitted at each frame. So this makes it harder to do inference or lattice generation in batches. What we do to solve this problem is first to make the infinite context into a finite context. So we simply replace the LSTM-based prediction network with a convolutional layer. And in literature, this is usually known as a stateless decoder, although that nomenclature is a bit icky. The other thing that we do is make the lattice monotonic. This is also an idea that has been explored, and this is known as monotonic RNNT or monotonic transducers. And the idea here is that instead of allowing the lattice to have any number of tokens per frame, we limit it to generate at most 1 token per frame. And this will naturally allow us to have batched computation. So combining both of these, we get the nice output that now we can have recognition lattices generated even for these nice transducer models that are very popular in industry and academia. How we do this is we again take the output of the transducer and we compose it with a very trivial graph, which is just a 2-state FST. And we get the recognition lattice that you have been seeing so far. Something else that we can do here is to bring in external knowledge. This again goes back to what we have been talking about encoding external knowledge into the WFST. And this is done by replacing the trivial FST that I showed earlier with a more complicated graph. So in this case, it's a LG graph, which has a lexicon and a language model. And the effect of this is that we have some prior encoded on the scores on the arcs. And the other outcome here is that instead of having a lattice which has tokens on the arcs, we have a word lattice, so we get the words directly. Let's look at some results, and I'll show results on segmented Tedlium, so we're not in the long form domain yet. If you look at the decoding time, first if you look at the beam search, a regular beam search for a traditional transducer without the monotonic constraint, the beam search takes a long time because we cannot batch it. But as soon as we add these constraints of monotonicity, and finally we can even use the WFST-based beam search, there's a huge improvement in the decoding time. And this comes at no cost to the word rate. So we are still doing reasonably well on word rates and even improving them for several cases. What I would like to draw your attention to is the last row here, which performs LG-based decoding with the transducer. And you can see that this performs much better than the ones above it. And those ones do not have any external knowledge. And here we have included external knowledge in the form of a language model. And this helps it to get even better word rates. When we do come back to the domain of long-form ASR, as Jenny mentioned, what we do is chunk-wise inference. So here on the x-axis, we have different chunk sizes. And on the y-axis, we see word rates. So you can see that there's a natural sweet spot somewhere around the 20 or 30 second mark. And this is probably because the model that we see here is trained using the original segmented utterances. So the curves may change somewhat if we go with training with fixed size chunks. But the conclusion here is that, again, the LG-based decoding is much better than not decoding with a language model. So far we have talked about word rates. But one important thing when we are talking about long-form ASR is also to talk about segmentation. And this is not a problem with offline models because offline models have the benefit of the full context. But when we're talking about streaming models, this becomes a big problem. And it's because of this reason. So if you think about the lattice that we are training with, the problem is that suppose the oracle alignment is the one shown on the left, we are not really penalizing the model, even if it uses the alignment that's shown with the red lattice or red nodes. And this leads to some problems, which you can see here. So the columns denote an offline model and a streaming model. If you look at the word rates without segmentation, so the first row, there's not much difference. We go from 6.2 to 7.6% word rate. But if we look at the word rate from computed with SCLite, which also penalizes segmentation, there's almost a 2x increase. And this is mainly because we are emitting the tokens much later than it's supposed to be. So in this case, almost half a second on average. So this naturally brings us to the third problem that Ehsan mentioned, is the problem of metric. When we are computing when we have a streaming ASR, there's a lot of latency which can be denoted to several aspects. The first is, of course, the input. So it depends on how much context we are feeding to the encoder. The third is, for example, the size of the neural network, which affects how much time the computation takes. But most importantly for us is the latency associated with modeling. So in this case, for example, if you have an alignment that I showed earlier, which does not penalize any latency, then you could have something like this, where the word is indeed correct, but it's emitted much later than we want it to be. And this is what we want to penalize. For this, we propose this idea of streaming edit distance, which is just a modification of a regular edit distance. And what this does is to add a streaming cost if the word is correct, but the emission time is later than an expected emission time. And the simple modification is the one shown on the red here. Of course, if you remove this red part, you get back your edit distance. Let's look at how the nature of the curves change if we compute the streaming edit distance for several thresholds. And this is for the Ted Liam dev set. We have results for 3 different models: regular, monotonic transducer, and another monotonic transducer, but trained with some delay penalty. And you see that as we increase the thresholds, that we are penalizing the model for delay less and less. We eventually get to the regular word rate, which is on the rightmost extreme. The other advantage that if you have this kind of a curve, it becomes easy to select models based on the operating point. So if you want to penalize models a lot, for example, if you want to set the model, the threshold to 0.5 second, we see that the monotonic transducer does much better than the regular transducer, but for a higher threshold, they do pretty much the same. In addition to it being a metric, we can also think about it as an objective function. So those of you who are familiar with minimum base risk training would recognize this as an instance of that objective. So in this case, we use the streaming edit distance as the risk function, and the derivative naturally falls out of that. First, very quickly, an important consideration here is how to use this during training. And for that, there are 2 things that are important. First, to pick an appropriate number of hypotheses very quickly. And the second is to compute the actual risk function quickly. And for the first one, we can again use the fast beam search, which I showed was much faster than doing regular beam search. And for the second, we have an efficient CUDA implementation, which is about 100 times faster than an equivalent C++ implementation. Now, of course, this is all available on GitHub. Of course, I'm not showing any results with this training yet because it's still ongoing. But something else to think about for the FST lovers out there is the word rate computation can be naturally interpreted in this form using something called a Flower transducer. So can we have some kind of different semi-ring modification to have the streaming edit distance computed in this fashion? So with that, I'll leave it to Tina to talk about beam search methods.
Thank you, Dash. So I'm going to talk about the beam search strategies for globally normalized models. So as you know, the inference rule for ASR is just to determine the output label sequence with highest probability among all possible label sequences. Now for the GNAT-based model that is basically doing the shortest distance, which means that in order to determine the path with highest score, we would need to visit the whole lattice. As an alternative, we could think about visiting only part of the search space that contains the paths with highest probability and prune away those paths that are less likely. And this is basically what is done in a simple time-synchronous beam search, where at each time step, based on the partial hypothesis scores, we can select, let's say, k number of hypotheses that we keep, and we prune away all others. Of course, if you have a locally normalized model with different heuristics that we already know about, we can actually say that this type of beam search is a good approximation of the whole search space, and we can get reasonable results. However, for the globally normalized model, we see for the problem that Ehsan mentioned earlier, we see that we cannot match the shortest path order rate even with a larger beam sizes. So let's look into an example. I have again the lattice that Ehsan showed before. So we have the sequence AB, and the shortest path will find you the blue path here. And let's say we want to perform a beam search of k equal to 2. So we want to, at each time step, just keep 2 hypotheses. So we start, and as you can see already at the first step, we will have these 2 arcs that have higher weights. We will select them. At the next, we will look into all outgoing arcs of these nodes. We will combine their widths with the partial weights that we had, and we prune away again. And we will end up recognizing actually the sequence A, which does not match. Now, if you look at this lattice, you can see that if actually we could have the information about, I think this finished the battery, probably. If you look at that outgoing arc from the node 1A, so that has actually a high probability, high weight, and if we knew about that already at the first step, then we would have been able to select that hypothesis. And this will remind what I presented at the first, let's say, part. That is, if we had the weight pushing algorithm, we could have already solved the beam search problem. Thank you. However, here, we have a streaming model, and we do not want to perform the weight pushing algorithm. So what about we just look at a kind of local reweighting? And what we are interested in are solutions that are distribution invariant, which means that we look at a context state, then we take, let's say, part of the weight, let's call it a potential, from the outgoing arcs and give it back to the incoming arcs. As you can see here, basically the probability, I mean the weight of this specific path is not modified on the path, on the sequence level. So we investigated 2 different types of potentials. One is a time-dependent one. You can see this as a kind of look ahead, an n-step look ahead, 1 step or 2 steps. This is what we looked at. But this needs still calculation during the decoding. We might want to have a constant potential that can be even calculated offline. And for this, we actually looked into something that I would call a mother prior. So what you do is that you look at the outgoing arcs at each context state, and you, for each of the labels, you basically average over the weight over the time. So now let's see how this actually solves our problem. Let's say we have a 1-step look ahead. We go into each node. As an example, we can look into the outgoing arcs and take the max over it, but we can also take the sum. And what we do is that we transfer this from this outgoing arc. So we subtract it here and give it back to the incoming arcs. Now let's see what happens to our beam search. As you can see, now this is the reweighted lattice. And our beam search already at the first step could select the right hypothesis. And in fact, we will end up having the correct one. Here's just an example of also the time-independent potential, just to see how for two certain arcs that, for example, an arc that is between the same label or different label, you will have this kind of subtraction and addition. Okay, now what about the results? So here I'm reporting word error rates for a transducer model with context 2 that was trained on LibreSpeech 960 hours. And the word error rates are on test other. And you're seeing three methods. You are seeing basically the end-step look ahead. This just changed. Oh, okay. The end-step look ahead for 1 step and 2 steps, and the model prior. You can see this as a 0-step, let's say, look ahead. And here you can read these results in 2 directions. So of course, as you would expect, when you have larger beams, you will always get improvement in your word error rates in each of the methods. But what we are showing is that also when you have more information on the, let's say, time direction, we are showing that you can get a better performance. And as you can see, while the baseline model stayed at 10.8, already with beam 32 and look ahead 2, we could match the shortest distance word error rate. So now as next steps, we would like to look into so of course we showed that we can match the same word array as the shortest path, but we would like to look also into other type of potentials that are not time dependent and do more analysis on the search and model errors. And here I give the microphone to Salah.
Sorry, there is a question from Michael.
Yes.
But he left the workshop to ask questions online.
Hi, Michael.
So, is the look ahead only used for the pseudo pushing, or is it also used in the local model to make a fair comparison? Yeah, in the local case, you get to look ahead in the audio context.
I didn't understand the question. Sorry. Can you read it?
Okay. Is the look ahead only used for the pseudo pushing?
What do you mean pseudo pushing?
I don't know. This is what you were explaining this.
I'm not sure about the pseudo pushing part, but this is done basically given the lattice. You can just rescore the whole lattice and then perform the beam search.
I think you mean local and global comparison.
Sam wants to say something.
No, it's just used for global.
It is just used for global. Okay.
Okay.
There is another question there.
Oh, that is a question, that whether we need, if it was the, okay, sorry, I could not understand the question. But I don't think really the locally normalized model would, I mean, I assume that with larger beam, we can match the shortest distance word error rate in the locally case. So that would be the difference. Of course, the weight pushing also in the locally case helps, but mostly for speeding up the search. And this is a slightly different problem. Anyhow, I now give... Oh, okay.
Sorry, I have one more question. So on the slide, I think 170, two slides back, you showed the prior model. And the question is, maybe I got it wrong, but can I think about it as a language model on like audio states?
Oh, that's a good observation. Yes, you can see this as a kind of, let's say, context-dependent prior. So this is actually, the idea is coming from when in the hybrid HMM model, you can just estimate the prior by averaging over your data. And here, your model is context-dependent, which means that the averaging will give you an n-gram prior for your good observation.
Thank you very much.
Any other questions? Locally, globally?
Go ahead, otherwise.
Hello, everybody. I guess you're all tired. I'm also tired. Even the controller seems a little bit tired. So bear with me. It's the last technical part of this presentation. And I prepared a very easy ride that is appropriate for 5 p.m. minds. So we'll be talking about what happens after ASR, also with lattices, but what happens after, so in the pipelines for the downstream task. This is why you have this small René Magritte picture. It's because it's pipelines and representations. So yeah, for the connoisseurs, they may appreciate. So we'll be talking about intent classification. So a classical cascaded model would first do the ASR, take the textual transcription, then give it to a natural language downstream head, and then you'll get the intent. We do not want that. Our project is to replace the textual transcription with a lattice-based one. And this has a few motivations. First, we do not want cascading errors. We do not want a model that would fail in the ASR and then would fail in the intent. And the lattice gives you all the possible paths with different probabilities there. We want portability and modularity. Focus a little bit, we'll be back there. We want to be able to change the ASR part, so what we call here the upstream head, without changing the downstream head. So we want our model to be modular. Something could change, like an old car. And the third one is we want a differentiable pipeline. We want to be able to differentiate only with intent on the whole pipeline. So let's understand a little bit the task we've been dealing with. So Slurp dataset, you heard about it. I'll focus on the ASR part. It's crowdsourced recordings of non-native speakers with noisy environment. It's actually, the word rates are pretty high. So you can see that even a model that is state-of-the-art on LibriSpeech would reach 54% word rate there. And the intents are presented here. So if you have an audio that says, can you put the vacuum on? You should get the scenario and the action. You can see it as a phone-oriented intents. Like you would speak to your phone, the scenario would be the app more or less you want to call, and the action would be the action on that app. So here it's IoT for Internet of Things, and the action is cleaning. So in the data set, we have 18 scenarios, 54 actions leading to 69 different intents. In this work, we'll only be dealing with classification. We won't be dealing with the slots, the entities, or other things you may have seen if you worked on spoken language understanding before. And we suppose that the training transcriptions are not available. We do not use the textual transcription of our intents, of our audio segments. So as I said, if the word rate is high, then the cascaded systems fail. So you can see on the left that the word rate is high in a lot of cases. So we have a lot of points where the word rate is higher than 60, 80, and even 100. And on the right, you can see that all the models that use textual elements, so either n-best or 1-best ASR, with or without language modeling, they are pretty good when the word rate is low, but they are very bad when the word rate is high. So let's get a little bit more intuition about this data set, talking only with textual inputs for the moment. So what we've done, this is the pipeline we'll have in more or less all our experiments. So here we have textual input, so we embed it, then we have the encoder, then an attentional puller, then a classifier to get to one of our intents. And if you input the true text, so the true transcription, the task is fairly easy. You would get 91% here, but when the transcriptions are bad, when it's the best ASR from a LibriSpeech trained model or the n-best, here it's 5-best, you would lose between, let's say, 25 and 20% in terms of accuracy. Some people would say, okay, but let's get some linguistic information there. So we replaced the embedding layer with a pre-trained language model. Here it's a BART large model. And if the text is good, then yeah, it improves the results. Actually, you get the semantic information, you get 2% more. But if the text is bad, it's actually even worse. Like you have words that do not exist, you get their semantic information, and their semantic information doesn't help you at all. So that's why we wanted to propose a lattice-based, that's one of the reasons we wanted to propose a lattice-based input. It's not exactly a new idea. A lot of people try to put lattices as input, but they were generally focusing on pruned lattices or word confusion networks. So one major difference and one major novelty in our work is that we would put the full lattice. And this actually gives an accelerator-friendly representation because it would be a very regular matrix there compared to word confusion networks or graphs. And we want it to be at the character level. It's not at the word level. So in every state, you would have context 2. In the context 2 scenario, we would have 2 characters. So this gives us this input, which is 3-dimensioned. One dimension is the time dimension, the second one is the state, and the third one is the vocab. And let's a little bit more intuition about all of this. Let's focus on one time step. One time step would give you this 2-dimension matrix with, for every state, all the arc weights that go out of that matrix. And to get back into the model I presented to you just before, if you have a 3-dimensioned input, you want to have a pooling function that would lead from a 3-dimensioned input to a 2-dimensioned input. And that pooling function is something we worked a lot on during those 6 weeks, and we think we got a pretty good solution. for that pretty good solution, we used forward probabilities. So this is the main, maybe, FST part of this representation. So bear with me, I'll re-explain even for the people rusty a little bit about the forward-backward algorithm. But we were using what people generally call alphas. And the motivation, so alphas are for every state more or less the forward probability of getting into that state. And the motivation is to get non-local information. So we would know for every state, we would have information for every state about the probability to reach that state in the lattice. And the other motivation is to get some topological information. Because if you know the alphas and the lattice, you basically know from every state where are the arcs here going. And the quick reminders about alphas, as I said, for people that would be a little bit rusty on this. So suppose you want to compute the alpha of this cell here. So it's a forward algorithm, so it's recursive. So we would need to compute the alphas of all the parents. So here we would compute the alphas of all those brownish cells there. And then we would sum those alphas multiplied by the weights here, and it would give us the alpha for that cell. And this is the values we would try to use as well as the arc weights as an input for our pooling function. What's the pooling function exactly? So let's a little bit get the setting before. We have a bigram context, so in every cell we actually do not have one letter, but we have two of them. And we have, as I said, a character level vocabulary and a locally normalized lattice. And how do we pool the three-dimensional representation? We actually learn for every couple state edge. So here you have a couple state edge corresponding to the sequence BOB or Bob. For every state edge, we learn an embedding. And this embedding is weighted with two things. First, the arc, the weight that is on the arc that goes on BO, and the alpha probability to reach that state. So the alpha probability to actually reach that BO state. And this, with the embedding and with this sum over those alpha probabilities and the arc weights, we get from this representation that is three-dimensioned, a two-dimensional representation. And this is done mainly in the with the Google LAST library, while the rest of the pipeline is done with a SpeechBrain library. Let's get now to the results of all of those. So as I said, we use an ASR upstream that is pretty bad. Like the word rate is pretty high, as you can see there, it's 54%. And we can see here the baseline. So the baseline, it's true text with language model, 1 best, 5 bets, and even one word confusion network we took from the literature, and logmails as a very bad baseline there. So if we have a look at our results, we will show the results with lattice-based inputs, only the weights, the lattice-based inputs using the alphas, and the encoder output, so the pre-lattice representation. The first conclusion is that lattice-based inputs actually allow to reach a way better performance than 1 best or n best textual transcription. A second conclusion is that adding the alphas actually give us a huge improvement. So you can see here that with the alpha we reach 77.3% indent classification accuracy compared to 66% for a 1 best textual pipeline. And the third one, though, is that if you use the pre-lattice representation, so the encoder representation, you actually have a pretty competitive performance. This is also the case for streaming models. So generally, streaming means that you will try to emit the ASR outputs as the speech comes. And as my colleagues have said, especially Hassan, I say, it impacts very severely the quality of the encoder, but also the quality of the lattice and the textual inputs, obviously. And even in the streaming scenario, even with a streaming ASR model, we can see that the lattice-based inputs weighted with the arc weights and the alphas is the best performing here compared to the encoder, and obviously way more performing than the textual inputs. So the question is, where does the encoder fail? Because we want it to fail. We want to promote our lattice-based inputs. So it fails on the other properties that we're looking for. And the main property it fails for is portability. So as I said, portability, you want to be able to change your ASR upstream without changing your downstream head. And text is very, very portable. If you take a model that is bad, that gives you a false transcription, then you replace it with a new, better ASR that will give you the good transcription, then maybe your same old downstream head will actually give you the good transcription this time, and you will improve. But what about encoder representations and what about lattice-based inputs? So here, what I'll do is we will replace the ASR upstream that has been trained on LibriSpeech with an ASR upstream that has been trained on a way larger model that is Speech2. Speech2, if you do not know it, is this big mix of all your favorite English ASR data sets. And it reaches a better word error rate on Slurp than LibriSpeech, so it's a better ASR upstream model here. And obviously the downstream head, if you could follow, is kept unchanged in this experiment. So here you have all the results that I have shown in the table before, but in a bar plot. And now you have the results after portability. If you do not see the encoder, the last column, it's not your eyes, it's basically too low. It reaches now almost random performance. While our lattice-based inputs with alphas actually improves and reaches the highest performance in our baselines. Another thing you should pay attention to is that, as I said, text is pretty portable. So when you improve the ASR, even if you keep the same downstream head, the performance with text starts to be competitive there. So as I said, we want the competitors to fail. I mean, we're not doing that in purpose, but they fail. So let's look at the third desired property, and it's differentiability this time. So if you do textual transcription, at some point you will take one best or n best. One best or n best involves a max operation. So here you would lose your differentiability. But if you take a lattice-based input, then actually your pipeline is differentiable. So let's differentiate. If you're paying close attention, you would see that I divided the ASR upstream to an encoder and a decoder because we're using an encoder-decoder architecture. And what we'll do in this experiment is that we'll keep the encoder frozen, but we'll differentiate the decoder on the intent classification task. We're still not using the transcription. Let's be clear about that. And why do we only fine-tune the decoder? It's basically to keep it close yet to some ASR thing. We do not want to lose everything that has been learned in the first phase. So when we do that, when we are able to differentiate, we actually have an improvement in performance. Not huge, but you can see that if you differentiate if you're only focusing on that downstream task, you can get improvements in the performance here. The bad thing is that if you differentiate, then you're changing the encoder. So your final input when you do portability is actually the encoder inputs. And you have a cost. If you differentiate, you have better performance, but it's not portable anymore. So you lose portability in a way. So to conclude, we have proposed a new full lattice-based input. It allows the three things we wanted: high performance in high word error rate scenarios, high portability, allowing for modular systems, and the development of differentiable pipelines. And I'll leave you here with the GitHub link and a graph showing that we do not fail that much in high word error rate scenarios with the lattice input. So, Luca. Your time. Okay, questions. Yeah, sorry.
So, did the lattice introduce any latency?
We haven't took that into account, but yeah, for sure. I mean, the lattice is, if we get back here, the lattice is way bigger than the encoder. So we have already a bigger representation than an encoder representation. For text, the latency isn't that big, to be honest. I mean, you have some latency on the downstream head, but I mean, if your ASR model is big enough, your downstream head shouldn't be the main part. But from encoder to lattice, you actually use the decoder, so you have this first cost, and then you have a bigger input for your second part. Like it's bigger. But the pooling function also helps to alleviate a little bit that. If you do not pool at all, then you have really a way too big input there. But yeah, it's a small trade-off. We haven't talked about it.
One more question about about the portability. Like, have you what are your thoughts about using the adapters, between it's getting quite popular, right? Having the speech encoder, some adapter, and some large language model, both encoder frozen, large language model frozen, and training just the adapters.
The only problem with the adapter in terms of portability, full portability, is that it needs a new training. Like here, it's a portability trainingless. Like you would completely just change this thing, and just change the upstream head, and you would have a better performance. If you do an adapter, basically, here you would need to train this small model again here, and would have it. You could think of it. You could think like here it's a small downstream head trained on Slurp. But suppose it's like it's a project we had with the Google team. Suppose it's the voice search downstream head. You do not want it to. You do not want to retrain it again. So think that every retraining here is pretty costly. Every retraining that is related to the downstream head is pretty costly. Here you really are completely trainingless. You change the upstream head and that's it. It's like a completely other team in the world. I don't know. OpenAI released Whisper. You take Whisper, you put it there, and that's it. I mean, Whisper is not FST based, but you got my idea.
There is a question from Michael. Is the pooling to reduce the intent input size? And I guess yes.
Can you repeat?
Is the pooling to reduce the intent input size? Yes. And is possible to not pool and get better results?
I tried it. Yeah.
So it is possible, but it doesn't work.
It is possible. You get more or less the same results. If you don't use the alphas, even if you do not pool, you actually do not get the results that we have there. But you could actually have two parallel ones, one with the alphas, one with the arc weights, and this leads to the same performance. But at that point, you're starting to lose a lot in terms of latency, as Andre pointed out.
You said, Michael, you should have stayed here.
All right, so it's pretty late, so I will be very brief, and so let me just wrap it up quickly. So in this afternoon, you have heard about many things related to finite state transducer. So we went through we have revisited the FST framework with through the lens of linear algebra and representing FSTs as tensor. You have shown in the second part, Ehsan has introduced the last framework which tried to use FST to provide a unified probabilistic modeling of ASR, solving many different tasks. And you also have seen application of FST in real life, for real case, I mean, not limited to, but including long form streaming ASR, pronunciation of OV words, training early exit model, and so on. So this is many things, but maybe if I hope that you remember something from this presentation is maybe two things. The first thing is FST can be interpreted as tensor. So this statement has some implication, and the implication is that it naturally fits with a neural network. Whether you represent it as very sparse tensor, or you do choose a way like last where you compute the FST on demand, at the end of the day, it's the same. Like FST are not opposite to the end-to-end system, and there is a huge benefit actually to use this technique to add them into a neural network pipeline. The second thing is I want to remind you that here we are not trying to lower the word rate. We are not working with FST just to get like a 1% absolute word rate. What we are trying to do is to do things that people can't do with end-to-end system at this stage. So we are trying to do more. And I think I really hope that we quit the ideas, its hybrid system is something of the past, or doesn't make sense actually. The tools have evolved, the computation has evolved, and there are a lot of things ahead using this kind of technologies. So this is not an end, this is just a new beginning. And I feel that here within this workshop, we've actually put the germs of, I hope, a long-lasting idea. And probably it would be a little bit unfair to claim that we are the one, because there was, as I mentioned, work done before. There was K2, there were the work of Annie and on. So let's say that we are just a continuation of this idea that seems to be more and more prominent in the field. And I think that starting from now, we'll see basically, we'll develop new algorithms that really allow this integration, and we can go much beyond from CTC or MMI and do much more things, much more complicated things, and more powerful, and build more powerful systems. So what next? Well, there are two tools that are, so LAS is probably usable. TensorFST is at this stage more or less a prototype, but if you're really interested by the topic, I really recommend you that you follow the update of this system. And to tell you how excited I am, I even created a Twitter account for the opportunity. So there are a bunch of upcoming publications. Oh my God, I'm so late, I'm getting to Twitter when Twitter doesn't exist. So there are a bunch of upcoming publications. I think the reference of the member of the people, I just feel free to follow them. And also, I want to say that we started to answer questions, but we have actually opened many more new questions. I don't want you to read it. I just want to say that there are a lot of questions that this FST challenge is actually raising, and I'm seeing there are a lot of work to do ahead. Let me finish with some little bit of advertising. I have money to spend on Tensor FST, and I don't have anybody to spend money on. So if you're looking for a postdoc, or if you're visiting, hey, I'm here. Talk to me. And maybe final word? I think we managed, right? It's not a final question, actually. I wanted to say two things. So I've participated to several iterations of the JSOLT workshop. Let me say that some iterations are good, some are great. And I want to say that this year was really great thanks to the organization. It was really nice to actually be able to focus on your science. So I want to make a big thanks to the Le Mans team. Actually, it was a really nice workshop.
All right. Do you have any last questions for Luca's team? No? Okay, then we'll get to a few closing remarks. And while I'm switching to those slides, let's do some physical exercise. Everybody stand up. Stretch your arms. Stretch your arms. Turn left. Turn right. Arms down and sit down again. All right, so everybody's awake for the important part. All right. Okay, so closing remarks. We heard from 4 teams over the last 2 days. We heard about FSTs and how they're great again. We heard about how it's always better together, and there's a GitHub for it. We heard about interpretable or explainable diarization, and I think I finally know what the team is trying to do, which is good. They explained what they're doing. And last but not the least, we heard about how to take a big gob of conversational audio and make some sense out of it and create some FST-like structure on how the dialogues flow. So I won't repeat all the accomplishments. You heard them from the teams themselves. I will tell you what it took to get there. It took a lot of people. So you've probably seen this slide before, but now you should think about it. There were 64 people who were here in Le Mans full-time, and another 20 people who participated remotely and were here for part of the time, sometimes 3 weeks, sometimes 1 week. And even if I completely ignore the people who were only in Le Mans part-time, and if only think about the 64 people who were here full-time, and I only assume that they worked like, the normal work day, which is not the case, and I ignore everything they did before coming to Le Mans, this is still 10 man-years of woman-year or person-years worth of work. So that's how much work we have done over here. So if you had a team of 10 people, it would take them a year to do what you've done here. So this is terrific, and this is something that anybody who thinks about sponsoring the workshop should realize. This is really good value for money. It's a lot of work that gets done here. Of course, we have a demographic breakdown. We're doing okay with students and senior people. It's almost half and half. We're not doing so well with women. Maybe we should help ask the women here to tell other women what a great opportunity it is, and they should come here. And if we can do something to make it easier, we'll do that. So please tell us. Again, in terms of who all we got here, again, you've seen this map before. Anthony put it together very nicely at the beginning of the workshop. We have people covering a big chunk of the globe. And I think after a long time, we've managed to get back into South America, draw people from there, Africa. Asia, we've always had some, but not from Malaysia. So that was the first, and so on. Anyway, so this is who we are. This is what we've done. So congratulations to all of you for these terrific accomplishments. And also, we didn't just do research. Remember, we spent 2 whole weeks training students, so hopefully all the students who go out of here know a lot more about the field than just their own little specialty. You know about deep learning, machine translation, large models, NLP, WFSTs, conversational systems, diarization, explainability. You're basically experts on pretty much everything in the field now. So go ahead confident that you really know what's going on. Of course, it wasn't just the tutoring. We also heard from a whole bunch of external speakers. So just think about it. 8 people came and gave us lectures, plus 4 people from the workshop. So you heard 12 seminars in these 8 weeks. So I don't know how most universities are, but in my place, like, a seminar every other week is considered frequent enough. So this is a lot of activity. There was a whole day on data collection and issues about data ethics and annotation and so on and so forth. And we had a nice discussion with a number of both data consumers and producers about, like, radio stations and so on and so forth, TV outlets, how they think about data, right? Of course, we were not just working. We had a pretty busy social calendar. In fact, we started on the very first day when the summer school began. Oh, wait, okay. All right, too many social activities. Right. So anyway, we started off right away with welcoming everybody. The students in Le Mans put together a barbecue picnic. Then we had a farewell pizza party at Barouf, and I think everybody now knows Barouf inside out. We had our welcome reception right here in the lawn. We had the guided tour of the old city. There was a street art festival, and we went to the Le Mans Classic race and saw the old cars doing it the old-fashioned way. We had a pizza party here to celebrate 4th of July, because I know we are in France, but we still celebrate American independence. And then, of course, we had a musical evening at Anthony's house, which I don't know how late it went, I think till 4 in the morning. And then, I don't know, I think Anthony went to bed at some point. I don't know how long it went. And then we had Marie and her band, Romela, playing Baltic music. And then we, of course, had the mayor of the city invited us to a party at his place to celebrate on the eve of the French National Day. And one music party wasn't enough, so Anthony hosted another one. And that one went even longer, I think. And then last but not the least, we have our farewell dinner tonight. And we'll hear more about that in a minute from Emma. So, actually, I forgot. There was that day where we had the neck massage. And then, and one more. I think we had Allomedia had a reception where they had wine in the lobby. Yes, so, okay, 2 more. So that's like 2 social events a week. All right, and I'm not even counting all the places you guys went, and you kept posting pictures on WhatsApp. So anyways, a little bit here. So this was the street art festival. It was not just another street art festival. The faculty here were involved in some of the art that got created over there and so on and so forth. So you remember this poster. Here was some pictures from the mayor's party. There was I think that guy over there is the mayor, I think. Like this guy right here. Yeah, so he was there. He gave a speech at his house or whatever, and then he even mentioned J-Salt, although he called it G-Salt, so I don't know if people recognized it. I mean, he said it the French way. We did other things, so these are, of course, pictures you'll remember. And by the way, Pablo did do fun stuff. He didn't just work. And I have a few more pictures. So these are our organizers. Meeting every now and then in the afternoon, trying to figure out what to do while all you guys are back in the lab having fun. So, and this is one of my favorite pictures from Le Mans. Right. Okay, so we're almost there. So we have to thank a few people. First of all, the organizers. So Anthony, Yenda, and I stand here and talk and pretend that, this is all our doing. Anthony actually does much more than me. But there are other people. Emma has been helping behind the scenes with many, many things. And also Anne Cecile, she is the finance person who fought many battles with the university administration to get you guys paid. There's, of course, Gregor, who you see every day or every other day helping us run this place with the audio, video, and all the technical things in the labs. And Etienne, who helps with that as well. Allomedia, Mano was here a few minutes ago. Okay. So Allomedia, 2 people worked to organize many things on the back end with the logistics. And of course, at Johns Hopkins, Ruth was the one who got a lot of the initial stuff going for the team meetings and so on and so forth. So let's pause and give these people a big show of hands. Next, we need money to do all this. So Hopkins and the Esperanto grant at Lamont are the two big sponsors of this year's JSOLT. As I mentioned to you before, it's about, let's say, 45 each. But then we got a lot of help in little ways from other people. So for example, these two companies sponsored a lot of the social activities during the summer school. These guys sponsored some of the expenses related with the data connection and annotation effort. And these two guys gave us cloud computing. So thanks to all the sponsors again. And the reason I thank them is because we want them to give us more money next time. Because next year we're going to be in Baltimore, right? So JSOLT, we had this formula where we said if we keep going away everywhere, we lose the sort of, let's just call it institutional knowledge that's needed to run these workshops. So Ruth and others at Hopkins remind us all the things we need to do in order to get this thing going. So I'm going to stop here, but since we have one more activity in the end, I'm going to give the mic to Emma, who will close out for the organizers of JSOLT.
Just some information to get to the Abbaye de l'Épau for tonight. So this is what it looks like. Well, it's a bit of a I don't know. I'm tired. Okay, so to go there, we can meet at the Prefecture tram station. I don't know if all of you know where it is. Yes, okay, so 6:30 to get the 6:35 tram T2. If you want to go earlier and have a tour in the park, you can go before, and we have some tram tickets for you if you go to see Anthony with a big smile, and they will give you a ticket. Just before the cocktail, we'll have the group photo. So it will be at, at 7 p.m. because we won't be there at 5 to 7. Then the cocktail on the sound of the Parair group. Then the seated dinner, and 10:30 we say goodbye and we all go home. And and so this is the map to go there. And it's on the website if you want a better picture. And have you registered? Well, come. No, it's a normal ticket. So if you already have some abonnement or something, you don't need one. It's usual ones. Okay, that's it.